Okay.
Okay, so I am going to start this presentation. Let me know if the full screen is visible.
Yes.
Great. So welcome everyone to the 2023 APS-CNM user meeting. We are joint workshop 3, so joint meaning joint between APS and CNM, the Synchrotron Nano Center. Our title is Toward Synchrotron-based Autonomous Scattering, Studies of Synthesis and Processing. Uta Ritt is the lead organizer, and John Mitchell and I are co-organizers. We're from 3 different divisions at Argonne. Of course, our focus, as many such workshops have been focusing on in recent times, it's what does it look like in the future? I think a lot of people have been asking this question, especially in the last few years. And the question becomes even more urgent in the last couple of months when ChatGPT came on the scene. What does it look like? What does future look like in a very broad sense? What does science research look like? What does synthesis laboratories look like? What does synchrotron facilities look like? I just did a quick search for science research laboratory of the future. The images are interesting. A lot of them still have the people. I love those giant displays like you see in sci-fi movies, but some of them have no people in them. This picture here, it's essentially all machines. So that's sort of a topic of interest, like what does it look like? So here are I would think of as overarching questions that we want to tackle in this workshop. And our focus is on the really excellent talks that we'll be hearing from all the speakers, as well as the discussion. I think people should speak up and ask questions and also give their opinions. What does autonomous experimentation look like today? I mean, I think a few speakers have really nice laboratories already. I want to hear about what they look like today, but what else is going to be important to develop? What else is under the works in the next 5-10 years? In particular for synthesis and processing. So at first we talk about synthesis, but we want to broaden it because what counts as synthesis I think differs if you ask different people, but just the idea of making stuff, making, processing, creating stuff, materials and chemistry. What are specific challenges for that in terms of autonomous experimentation? What are the roles of synchrotron characterization in that, and in particular scattering? We had really nice discussion, through email about what does scattering actually include. I think we want to see what everyone's point of view is in terms of what role synchrotron is going to play. And last but not least, quite important, what current capabilities in AI/ML should be used, can be used, has been used, and are there certain algorithms that would be really helpful, but it's not currently available. So that's with that said, I'd like to give a brief preview of the workshop schedule. This afternoon and tomorrow's afternoon, we'll have several talks, 3 talks per session roughly. We'll start with some thoughts about autonomous experimentation, both in terms of synthesis and also a synchrotron perspective. We're going to talk a little bit more about materials discovery, self-driving lab, and materials discovery in the second session. Tomorrow, we will, sorry about the bolding not working. We'll continue into more specific samples in terms of catalysis, for example, and polymers and some other examples, and also inject a bit of theoretical perspective in this. So with that said, I'll pass it on to Uta, who's going to chair the first half of today.
No, actually, you pass on to John.
John, oh, I'm sorry, I got that confused.
No problem.
Yes.
Thanks, Maria. That was a great introduction, I think. And so welcome everybody to the workshop. As Uta said, I'm John Mitchell. I'm the chair for this first session. I think we should just go ahead and get started. Our first speaker, we selected because we wanted to get sort of a very broad overview of the topic, and then will allow us to focus a little bit more narrowly as the workshop goes on. Benji Murayama is probably known to many of you as a kind of one of the pioneers in this idea of closed loop autonomous synthesis and autonomous discovery. Through his work with the at the Air Force Research Laboratory on carbon nanotube synthesis. And so I have a feeling that Benji is picked on a lot for this kind of role. So I appreciate very much him willing to take some time out of his busy schedule and kind of set the stage for us this afternoon. So I'm going to turn it over to Benji, and Benji, you have about a half hour. I tell you what, I'll try to, hop in maybe 5 minutes before and give you a little heads up, but otherwise take it away. It's all yours.
Great. Thanks, John. Thanks for the invitation. It's a great opportunity. I do not get tired of doing this. I'll tell you, it's such a fun area. Let me just start confirming. Can you see my screen okay? And you can hear me okay? All right, then let's go. Yep, so I'm going to talk about autonomous research systems, ARES, and maybe call it autonomous experimentation, self-driving labs. There are lots of different names, which is actually goodness, because that means that things are actually moving forward. Hopefully my cursor is going to work. Okay. And so Maria talked about people, and actually I'm going to focus quite a bit on people. And so, for example, we know that we don't have enough money. We never have enough money, but we actually don't have enough people, the right STEM workforce. And we're out of time in a lot of ways, right? Global climate change goals say that we have to get to net zero by 2050. Lots of other problems that are time-based, and our current way of having research take decades for advancement just doesn't work. And maybe the bottom line is that the demand for research far outstrips our supply. In the Air Force, General Brown gave us a directive: accelerate, change, or lose. That's in our 2020 strategic approach. We can't do things, we can't do business as usual. Secretary of Defense Mark Esper talked about AI and chemistry, but again, the people part is down below in bold. These advances free up time for our scientists and researchers to focus on next generation innovation rather than countless tests and experiments, and we'll come back to that. Okay, so what is autonomous experimentation? Our original ARES work on carbon nanotube synthesis was the first system that I know of for doing closed loop materials research. ARES was able to teach itself how to grow carbon nanotubes at controlled rates. I'll walk you through some of it quickly, and I'm going to use my pointer here. Hopefully this works okay. Oops, that's not the pointer. Laser pointing, there we go. Okay, so the first part of it is that we have these micro pillars, right? We hit these micro pillars 10 microns across with a laser, and the laser has two roles. First, it heats the pillar up to the reaction temperature for carbon nanotube synthesis. The second role is that the scattered light coming off of the pillar is sent to our Raman spectrometer, and from which we get our Raman spectra, and the results, we know what's happening because of that scattered light. So we have what we need to grow carbon nanotubes. We have the catalyst on each of these pillars. We have the hydrocarbon from the gas source, and then we grow the carbon nanotubes, so we see what happens. And from a flow standpoint, you can see we initialize our database, we plan an experiment. In our case, we used a random forest with a genetic algorithm solver. We conduct the experiment and get the raw Raman spectra, and then we turn those raw Raman spectra into a growth rate. So we do an analysis. And on the bottom left over here, we can see a series of hundreds of experiments where the black line is what we thought the growth rate would be. And then the colored dots are the experimental results, what the growth rate actually was. And this is on a log scale. And you can see after hundreds of experiments, there's still a whole lot of scatter. And then eventually, about 500 or so, it converged. It essentially locked on to a predictive ability for the rate of carbon nanotube growth. So then we generalize that to
okay. I found this on the web for a series of hundreds of experiments where the black line is what we thought the growth rate would be, and then the colored dots are the experimental results what the growth rate actually was, and this is on a log scale. You can see after hundreds of experiments.
It was on your end.
Yeah, no, that's my Siri who's interrupting. I don't know how to turn off Siri, but I might need to do that. Okay. So this idea then of closed loop iteration. So they're historically, right, our build up to autonomous experimentation was with things like high throughput experimentation, combinatorial experimentation, right? That's ways of doing lots of experiments. There are automated ways of doing experiments. So that's pre-planned experiments that were done without human intervention. The distinction for autonomy is that the system now is able to design its own experiments and learn from it. And it's able then to make decisions about what to do next based on prior results. So that distinguishes it from high throughput and combi methods, or even regular AI methods where you're sort of taking a database and doing some kind of a neural net on it, coming up with results, but it's still up to the human then to implement and reason over that to try and decide and act on what to do next. The other benefit for this closed loop autonomous experimentation is that now we can actually do experiments explicitly on hypothesis generation and testing autonomously. So that is when we, for example, plan an experiment, in the first iteration of Aries, it was just, hey, let's try and predict what the growth rate is going to be, or maybe maximize a growth rate. But you can also make the objective of the experiment system be to understand, confirm, or negate opposed hypothesis, right? So all those things are aspects of your experimental objective, at which point then you execute an experiment, and it doesn't have to be a physical experiment. It can be a simulation, it can be a characterization, much like the NIST folks do. Then you go out of the experiment loop into the analysis loop. So here's where you extract your understanding. You take time to try and reason and understand what happened, again, autonomously. And then critically, you go back and you iterate. And really, it's the iteration that gives us, I think, our superpower in this sense, that lots of iterations beats lots of experiments. And then eventually you can conclude. But this initialize and conclude blocks are human-driven, right? It's the human who defines the objective, specifies the constraints, and provides the prior knowledge. And then really sets the exit criteria and reports the knowledge and so forth. So I think that's really important there. Okay. And now we'll go here. So thinking then about artificial intelligence in science, there's a challenge now out there from Professor Hiroaki Kitano at Sony. Can we build machines that can win the Nobel Prize by the year 2050? That's a big challenge. I would note that Professor Kitano previously issued the RoboCup challenge, which actually drove the autonomy community for a number of years. But according to Kitano, there's a distinction between autonomy and intelligence. We often confound the two, but that's to say you can have autonomy without intelligence, and you can have intelligence without autonomy, right? And what's necessary, in his opinion, and I agree, of course, to win a Nobel Turing Challenge is the combination of both intelligence, understanding what's going on, and autonomy, which is that delegated decision authority to act, actually to do what comes next. And so according to Kitano, his assessment of our current state of scientific discovery is that we are at the pre-industrial revolution level. That is, if we were farmers out in our fields, we would be farming with hand tools and beasts of burden instead of what farmers actually do nowadays, which is to essentially use combine harvesters that are AI guided. So a huge difference there. Okay, so I won't go into this too much because I think a lot of people are talking, but there's a lot going on in autonomous experimentation now. I think we've reached our trigger point, technology trigger in the Gartner hype cycle construct. But this is Keith Brown's work at Boston University. So Keith has a robot that prints twisted barrel structures and puts it in an instron and crushes it and measures the energy, the toughness, the energy absorption. But what Keith did that's distinctive is that he actually quantified the speed up, showing a 60-fold acceleration with black box optimization and better than 600x acceleration with good prior knowledge versus your normal grid-based search. So that's to say that just doing more experiments is simply not enough. You really have to have that iterative capability. Self-driving lab. So this is Alan Aspero-Gusick, Curtis Berlin-Gued, and Jason Hine. They're doing very nice work with chemistry and different traditional sort of arm-based robots. Gilad, who's talking later, along with Brian DeCoste and previously J. Hattrick Simpers, are doing their Bayesian scientific AI. And then highlight Carla Gomez's work with Bart Selman, because they're really doing reasoning, and that is reasoning over, in this case, phase diagram space. So implementing, for example, Gibbs rules, phase rules, to decide what to do next, when to stop, what actually makes sense. So theirs is the SARA, Scientific Autonomous Reasoning Agent. And then more recent work out of Japan is this connected, shared, high throughput platform that's autonomous. So this idea of trying to start to connect tools together, which I think is significant as well. Then finally, Yolanda Gill, who's not a material scientist, she's an AI person, is thinking very abstractly along the lines of the Nobel Turing Challenge about AI and scientific discovery, and thinking about what AI agents will be able to do, reproduce articles, be research assistant, co-author as investigator. So that's sort of progression in her thinking. Sorry, and I'll skip over some of these. So good work at CMU. We have some work in our labs reproducing Marty Burke's molecule maker robot, which is a chemistry robot, but now is made closed loop by this inline NMR tool that's led by David Simone in our lab. So we actually have an Aries OS software that we've developed. Dalen Hooper, co-inventor of Aries, along with the rest of his team, are building an open source software platform that I'll refer you back to in a little bit, but it's very exciting for us in doing that. And I'll skip through some of these. Okay, so synthesis, back to carbon nanotubes, and hopefully this resonates with the Department of Energy folks. Can carbon nanotubes save the world? I'm actually talking with folks at the Rice Hub right now and Kavli about this very problem. So why aren't carbon nanotubes a commodity polymer? Why don't we have tanker trucks full of carbon nanotubes? Essentially, it's because we don't have the science to do it. The energetics, the available materials, there's no rare catalyst involved. It should be to the point where it's like polyethylene levels of production. How do you save the world with carbon nanotubes? So ARPA-E issued this methane pyrolysis program, and Rice and Shell effort was looking at how to take methane, which is currently burned to CO2 at hundreds of millions of tons per year, and thereby causing global warming, significantly contributing. And it's interesting, for methane, most of the energy is in the hydrogen. And if you pyrolyze the methane, you can send the hydrogen to the hydrogen economy. And of course, you could just bury the carbon in the ground, which is what some people are planning to do, but it's much better if you can make carbon nanotubes, at which point the carbon is sequestered. It's not contributing to global warming. And if we can do that at scale, it's a no kidding 20 to 40% reduction in global CO2 emissions, which is the save the world proposition. But we can't make the carbon nanotubes at scale. We don't have the science, we don't have the infrastructure. And that scale is really hundreds of millions of tons per year, where it not only does it change global CO2 emissions, but it changes the materials market. So very heady proposition there. And so just to think about what we've been doing for some of our nanotube effort, we've been working with Chris Reyes at the University of Buffalo, who I think also has a joint appointment at Brookhaven, and Rahul Rao at AFRL, where we think about his Holmes knowledge gradient descent policy on how to choose our next experiments. So thinking about where the maximum, not just reduction in uncertainty, but reduction in uncertainty towards a specified goal would be. And so with Chris's help, we were able to increase our selectivity of carbon nanotubes chiralities by 5x. Then again, we're talking about hypothesis. So we have this hypothesis that the state of the catalyst drives growth. It's well known that you need to reduce a catalyst in order for it to be active, but how much and for how long? And so we hypothesized that catalyst reduction drives CNT yield and chiral selectivity. And we built this essentially thermodynamic hypothesis that said that if we were able to pose the hypothesis in terms of free energy, which we can think of as, the traditional free energy equation where we have the activities of the reductants and the oxidants. So for us, that's ethylene and carbon dioxide versus temperature. And when we plot it in this temperature versus log K plot, we can see that the best activity lays along this, what we propose is the delta G equals 0 for iron oxide reduction, the catalyst reduction. The maximum of activity lies along that thermodynamic line. So we have strong support for this reduction hypothesis using Aries. The reason why we were able to do this so efficiently is because of Chi-Woo Park's work. He's at Florida State, and he has this jump regression tool. So there are lots of different decision tools out there. A lot of them use Gaussian processes because the oxide reduction is first order phase transformation. It's then discontinuity, and Chi-Woo's jump regression planner is made to go directly after discontinuities, to locate those discontinuities in as few experiments as possible. And so then what he was able to do, and again, this is sort of our thermodynamics plot, is to create this jump, as he identifies it, which very much lies along the line of that delta G equals 0 for iron oxide reduction. So that was the jump regression for a 1 nanometer catalyst. And then we used his jump regression plus transfer learning to look at a thinner catalyst. And then that also speeded up our ability to learn quickly about carbon nanotube synthesis. So just sort of a quick survey of different decision methodologies to figure out what your next experiment will be. So here I'm showing our additive manufacturing Aries, or 3D printer Aries in action. So it's printing out a square, in this case with latex, and then it has a camera, takes a quick picture and does an image analysis to see how well it filled in that square. And so we're able then to change the 3D printing parameters for each iteration to try to learn how to print in terms of things like the extrusion multiplier, the print speed, and so forth. And you can see after, sort of tens of experiments, it's taught itself how to print over a fairly simple structure. So that was an exciting result for us. So now I'm going to sort of go very high level and think about the future of research. I think hopefully it was very hard to see the introductions very much in line with what we're trying to think about. I think really, there is a step change in the angle of how autonomous is being reported in materials science journals. So I think we really are at our trigger point here. The MGI, Materials Genome Initiative, calls out autonomous research as well. So I can point you to that. And then something that Simon and others who are going to be here are part of is this Matter paper from now a couple of years ago, which really gives our community perspective on what we think the needed investments are, what the value proposition is, and I think it's still very pertinent, so I just direct you to that paper. Okay, so trying to go towards what we think of as a research revolution. I already made the analogy to the industrial revolution where farmers went from, beasts of burden and hand tools to tractors, right, to AI guided. So that's sort of the industrial revolution was the replacement of human labor, or the magnification of human labor, manual labor, with machine labor, with machines. The cognitive labor is really thinking about, say, compute, right? So human computers in the 1940s were humans, mainly women who were calculating trajectories for NASA or firing tables using calculators and, sort of longhand math. And then, of course, there was the mainframe computer that replaced a lot of that cognitive labor. And nowadays, we don't think of it as compute power. We just think of them as our phones that tell us where to go on GPS. So that's the revolution there, is that robots were able to perform both manual and cognitive labor. And for the research revolution, why hasn't that already happened? is sort of maybe the way we think of it sometimes. So if Madame Curie from the 19th century came and watched our research processes, the way that we hand pipette samples, hand load samples, hand polish samples, log things into our data book, our notebooks, why are we still doing those things manually? And also, why are we making these cognitive decisions on, say, an experiment by experiment basis? I would say that Ares, our original Ares robot, did a new experiment every 5 minutes. It's hard for a human to parse 10-dimensional parameter space over a complex response surface every 5 minutes, right? That's a hard calculation to do. So right now, what we're working at is AI research robots that can perform manual and cognitive labor 1,000 times faster, again, in partnership with humans. More with Alexis Lewis from the NSF about this research revolution with Eric Stack at UPenn. So, okay, now I'm going to shift gears again and think about what's wrong with science. So really, there's not enough of this included in doing research. And part of that is the headline here. Children lose confidence in their potential to be scientists, but not in their capacity to do science. We are losing people along the way, and especially the most, I guess, underrepresented groups, girls, minorities, lower socioeconomic backgrounds. So the people who are most underrepresented. So we need to figure out how to fix that problem. And really, we're failing our S&T workforce. S&T, people who are good at STEM, especially in the US, will go to finance, they'll go to software, they'll go to consulting. But once they're done their undergrad, that value proposition of going into graduate school and paying your dues for doing that menial work, that polishing of samples at, by the way, a training wage just doesn't work anymore. So we need to find ways to value our S&T workforce for their insight, their creativity, and their human intelligence, where they will increasingly go elsewhere. So with Marty Burke, we're working on this 1 billion scientist movement, and a core part of that is diversity, equity, inclusion, that more than just, sort of a DEI acronym, it's really imperative, intentional, and impactful. So how do we democratize science? Here's the thing. As we built these research robots, at first I thought it was about getting the human out of the loop. But really, autonomous experimentation is about people. It will free us to do research the way we want to do it. Thinking about the hard problems, thinking about how to attack it, how to constrain it, why it's important to do, and having autonomous research robots as our partners to do the kinds of stuff that we don't want to do, the dull, the dreary, the dangerous work. And there's a great example about human-robot chess teaming, where the human and robot teams beat humans or robots, i.e. software, all the time. But in the 2005 tournament, the winner was not the grandmasters with the best supercomputers, but the winner was a pair of amateur chess players with 3 computers who had superior teaming. So we really need, as we're building our autonomous experimentation systems, we need to also think about how humans and robots partner to do research better. And so part of that is, in teaming, is really division of labor, thinking what robots are good at and what humans are good at. And skills and ability, communication, trust, division of labor, delegation of decision authority. By the way, all these things are already being worked in the autonomy community, right? We're not inventing this. It's really about us having those discussions, having the interdisciplinary outreach to be able to talk to them and learn from them and actually hopefully get them interested in our problems as well. And towards the democratization of science, we're building this educational Ares system. So it will be an open source printer, 3D printer that we can deliver for $300 and lowers the barrier of entry for students. So at $300 price point, we can put it in schools and libraries and really start to build that future workforce in autonomy, AI, and materials. There's in the lower right is our Git link for Aries OS 2.0. It's now released, open source. And so Aries OS is really our open source software for anyone to use as a framework upon which they can build their own autonomous research robot. It's not the whole software, but it's a good framework that's built on a robotic behavior paradigm. And hopefully people can download it and use it to build their own research robot. Please contact me if you're interested in that. We're not the only ones. So Marty Burke from the University of Illinois at Urbana-Champaign has his digital molecule maker, where he's thinking about delivering molecules to the masses. And then maybe Gilad will talk about this later, but he and Ichigo Takeuchi at the University of Maryland, so Gilad at NIST, had built their Legolas chemistry robot using a Lego Mindstorm robotics kit, which is very exciting as well. So one of the things we're thinking about is economics of research and thinking about having a Moore's law for the speed of research, where the rate of research goes up exponentially over time. Anecdotally, I've had two different professors with a week's worth of time in my lab on Aries, and they each came to me and said, Benji, in a week's worth of time, I did a dissertation's worth of research. So let that sink in. 5 years worth of research done in 1 week. That's quite the speed up. Now, if we can continue to increase that period over period for the exponential growth, imagine what happens after that. The corollary to Moore's law is that the cost of doing research goes down. So the cost per experiment, it used to be we could do 1 experiment in 1 day, and now we can do 100 experimental iterations in 1 day. Since we're labor dominated in our cost structure, the cost of that experiment just went down by a factor of 100. So now experimentation becomes exponentially cheaper in the same way that compute power got exponentially cheaper with the advance of silicon electronics. So the impact of that research getting cheaper is that now more people can access research, right? Or if you have a $300 autonomous 3D printer, now lots of more people have access to it. And so with that, you then have a growth, an exponential growth in the number of scientists and a rise of citizen science. So that means that not just those of us with big labs and access to beam time can define the research agenda, but in fact, many more of us can define the research agenda. So it's not limited by the government or by private equity or whoever has money. Because it's less expensive, now lots more of us can do research. And by that nature, it improves our scientific community in terms of diversity, equity, and inclusion. So then I just ask you to imagine what would happen? What if we were a society of 1 billion scientists? So then just to sort of wrap up, we have then autonomous experimentation for human scientists. So it vastly multiplies the efforts of humans to do more and better research. It gives autonomy back to human researchers. That's sort of ironic, right? The autonomy sort of was delegated to the research robots, but in doing so, now the lab rats, as we're sort of called, have the ability to make their own decisions at a higher level, like what hypothesis do I want to explore? What hypothesis space do I want to explore? Really constraining and guiding the problem and defining the problem rather than sort of doing those countless experiments and analyses. And again, it enables more people to drive the direction of research. So I think what's needed going forward is this private-public partnership for autonomous experimentation. That's, of course, a partnership across government, industry, academia, and science and technology, but also impacting society and the economy. And there's a whole host of different problems that we can think about: climate change, quantum, AI and autonomy, S&T equity. And importantly, as we get these robots going, we can increase the rate of S&T transitions by driving down the risk and reducing barriers. And also, we modernize our workforce by having better access in citizen science. And finally, we can think about what's needed to do this, which is a true recapitalization. We do not have the hardware infrastructure, the software infrastructure, the human infrastructure to do all the things that we need to do. And so it's going to take quite a bit of investment to make that happen. So I'd like to acknowledge my collaborators and support from AFOSR and NRC, and hopefully I've left enough time for questions. I see something in the chat there, but I'll let John guide what we're trying to do.
Great. Thank you very much, Benji. That was a terrific talk. Absolutely hit the mark on what we wanted to give, sort of a broad view of what's possible, what's going on, and why it matters. So thank you very much for that. That's terrific. So we have about 5 minutes for discussion here. So I invite participants to either raise your hand, put something in the chat, or just speak up. But there's one sitting in the chat right now, so I'm going to start with that. And then Simon, I'll get you in a minute. So Uta says, wouldn't it be important to give everyone access to data gained by autonomous experiments to give more people a chance to contribute?
Absolutely. I think data availability is important. And I think, it's sort of interesting, right? Because our AM areas, our 3D printer is online, it's cloud-based. And, we can make that instantly available because our autonomous research robots are inherently digital, right? As Josh Schreier from Fordham says, our data are born digital, and we can make them available immediately. And that means that really going back to collaboration, that not only are the results available, but hopefully we make the planning algorithm and decision modalities available. So not just what happened, but why we made that decision, what were the expectations. So yeah, I think all of that will really enable more of us to work better together. Absolutely.
Great. Simon, you have your hand up? Fire away.
Yeah, thanks. Yeah, Benji, great talk as always. So I had one question and one kind of comment, I guess. The question is, in the democratizing scenario, the things that you seem to talk most about were that you could make low-cost platforms that you could probably make available in schools and classrooms and things like that, and then they could be run from your open source automation platform, let's say. But there's another modality for democratizing experiments, which is that you have some complex and expensive piece of equipment, but it's actually controlled autonomously, right? And that's actually what we're looking at with the facilities. But you could have people using it remotely more easily in autonomous fashion than they can right now. Is that do you agree with that, or you think that?
I do agree with it. Yeah, and I think I think having those really expensive resources and sharing them, I think is what the energy labs do really well with their user facilities. And I think, I guess I'll just sort of throw my opinion in there. Having done some beamline experiments, you go up with your plan A, B, C, D, and probably A, B, C are gone by lunchtime, and you're left with D, and then you have to figure it out for E, F, and G. But that you're making decisions on the fly, right? And so what if you then had a robot that could help you explore that complex decision space autonomously and do experiments faster, more efficiently, and in high dimensions to essentially maximize the use of precious beam time? Because let's face it, even if it's available to the world, you're only going to get a couple few days, per session. So you really have to make the most of your beam time. So that decision on each experiment carries a lot of weight. And so I totally agree with that. And I did have some sort of thoughts that I can talk to if there's time about sort of autonomous economics of experimentation. And, I'll just leave some of this up here to think about, but, how do we start to think, we always think about the science, but we don't think about the process of doing research. And how do we think of those in sort of economics terms about expected return on investment and benefit and cost and risk and all that kind of stuff. So those are sort of the top line thoughts that I'm thinking of. And I think they're, the beamline experiments and the user facility experiments are a special case of those that deserve a lot of attention.
Simon, since you have a half hour, you can make your comment during that half hour. I want to give Uta a chance to ask her question.
Thank you very much. So what I see with pleasure, but also, of course, with a kind of horror, is the true acceleration of science, what we see, right? I mean, research that was done in 50 years can be now done in 3 years with the latest methods we have, but now with autonomous experiments, I guess we can achieve the same in half a year or something like this, which is incredible. But my concern is a little bit, how can we catch up with it? And how do we assure the data quality at the end? I mean, we are really accumulating so much knowledge, which also becomes harder to use, right? But maybe it's a kind of spiral. So we need, of course, also autonomous ways to look through the data to come to the next one.
Right. No, that's really good points. So ethics are absolutely concerned, right? We want to make sure that because we make these more available, that that lowers also the barrier to potential bad actors, and we need to make sure that we have processes in place to stem those as much as possible. As soon as 3D printers came out, people were printing guns, right? So those things are going to happen, but we need to get ahead of that and understand where that can be. I do think that there's, of course, historically there's been lots of bad data out there. And it's just human, it's up to the humans to look at what was good and what was bad. But of course, we can't do that with these floods of data that we're expecting. And there's frankly, there's intentionally bad data that could be out there, right? We all know about news media and things that are corrupted and purposely misleading. So yeah, we have things to think about and figure out processes to jointly, flag data that are harmful or inaccurate. And I think that'll be a good challenge for the community.
Thank you.
Great. Okay. Thank you very much, Benji. That was terrific. We'll have a little bit of time at the very end of the day for follow-up questions. So I'm going to ask you to just go ahead and stop sharing your screen, and we'll get Simon to get his going. So while Simon's firing up, I'll just say, so I know that Simon's been thinking about this problem for at least a decade, because that's when he and I started talking about it a little bit in another context, and has been turning thinking into doing. And so I'm looking forward to hearing what he has to say about how autonomous and automated research at synchrotrons will take place. And so he calls his talk "Automation for Scientific Discovery, Beamline Experiments of the Future, What They Might Look Like and How to Get There." So Simon, the floor is yours.
Great. Thanks very much, John. The floor is mine, but I'm to rearrange my screen. I need an autonomous way of moving all the Zoom junk. Okay. So I think you should be seeing my display screen. So yeah, thanks very much, John, and Uta and Maria for inviting me. So yeah, I've been thinking about this for a long time, and we've started doing it. And I've been talking to Benji for a fair number of years now, and working together with Benji. And I share his excitement, and I really appreciate that he gives such a strong vision. A lot of the things I'm going to say are actually echoing what he said, maybe from a slightly different point of view, but then I will actually get into the facilities part of it. This is my goal, basically. So there's a lot of interest in actually in the broader community about materials labs of the future. So I'm very happy that we're having this workshop. And this is just one example, but this is an NSF supported, sponsored workshop that John and I ran with Suzanne Stemmer. So, and the title of the main workshop was Materials Labs of the Future. And what NSF is actually thinking about is what's actually the materials lab going to look like after our pre-industrial revolution types of labs that we have now. And the report is not quite ready, but it's about to come out, and it actually kind of told us that there's a lot of research that still needs to be done. There's going to be it's not a question of just investing in robots and then everything's going to work. We have to actually try and figure out how all the pieces fit together and communicate and add value. But it is a very exciting horizon that we're facing. I want to very strongly recommend this paper. It was a kind of a community perspective that was led by Eric Stack and by Benji, and I was one of the people involved, but many other people involved. But what's very special about this paper is actually it's very rich in all the aspects that Benji's covered, but also some of the more technical details. And I strongly recommend you to go and read this as a starting point. And Benji showed us that this is the basic kind of way that you would capture the autonomous methodology, where you initialize a thing and then there's a loop that happens and then you draw conclusions from it. But yeah, go get this paper and spend a bit of time with it if you're interested. So this is what the loop looked like in that paper, and it's basically you do a bunch of planning, then you actually do a bunch of experiments, and then you do a bunch of analysis and knowledge extraction, knowledge representation, and then you iterate that. Actually, when you break it down and you try and do it in practice, to me it looks a little bit more like this. It's kind of a 6-step process. What you do is you have an experiment that's been somehow designed, and you it contains a bunch of parameters that you're going to use for the experiment. So the first thing is to set those. Then you initiate an experiment, and once the experiment is run, you measure the result. So you need a way of actually interacting with it on the measurement side. You need to then make some assessment from the measurement. That's essentially, I'm going to go through these steps in more detail a little later, but you do an assessment. And once you've assessed, you decide, should I do another experiment or should I hop out of the loop? If you decide to do another, this is basically a go, no go decision. If you decide to go, you need then some kind of algorithmic way to design the next experiment, and then you iterate around the loop. So of course, this is this terrifying thing that Uta kind of mentioned, that actually, and everyone is afraid that we're going to just replace all of our grad students with these things, and there's not going to be any humans. Benji made this point. So this is what the human looks like, and this is what the human in the loop looks like. No, but that's just a joke. But this is actually how the human does science right now. So the human will ask a scientific question, and then if often we'll formulate a hypothesis that we want to test. Then we'll design an experiment that tests the hypothesis, then we'll do the experiment, and then we'll assess the results. So this is the kind of linear process that we're familiar with. And one way to look at this kind of automation process is that we actually just insert the automation part in this same process. So it's still a human being who's having the idea, deciding they want to do something. Largely speaking, the human being is formulating a hypothesis. Now they're not designing a single experiment, they're designing an experimental campaign. And then, of course, it's the human who has to initialize everything. So you initialize the parameters, but then you let the autonomous operation happen in this loop, and there's no human in this interior loop. And then you finally assess the results here. So I don't think we need to worry that, and it's really, again, reiterating what Benji said, that this is something that is going to enhance our ability to do science as humans. It's not going to replace humans doing science. I don't think that's even the goal. So I'm going to use as an example a very small proof of principle experiment that we did. This was actually, I think Karina's talking this afternoon, so I don't want to take away, in case she's talking about this, I'm not going to go into too much detail, but I wanted to use this as an example of an autonomous experiment at a beamline, and it's one of the earliest, if not the earliest, of them. So it was actually Pete Chupas and Karina who came up with the details. We were having conversations together as part of an EFRC we were part of, and then the postdocs Yevgeny and Daniel did much of the work. But if we go back to this this plot that I had, so the initial part is actually human beings asking questions and formulating hypotheses. So taking this panel from the paper that Benji also showed, the initialization part, you're going to ask a scientific question, formulate a hypothesis, design an experiment. So in this case, it looks like this. We said, okay, I'd like to synthesize a copper oxide material with copper in a certain charge state. So this is an example of our scientific goal. Actually, the real scientific goal of this was to do a proof of principle autonomous experiment in situ at a synchrotron. But our kind of fake goal was to actually get this putative copper oxide in a well-defined charge state. And so the hypothesis would be that under the right conditions of oxidizing and reducing gas environment and temperature, we'll be able to accomplish that if we can find it. And so then the experimental campaign was put together, and it used a lot of human intuition and chemical expertise from Karina and her group, and also technological side about how to put it together with how to flow the gases and to flow them in a pulse form. This is stuff I have no idea about. I think Pete Bess was also a big contributor here. So it's a team effort. There's a lot of expertise is involved. But basically, we've got something set up that's going to flow gas, and it's going to flow it over the sample. And then what we have under computer control is the different oxidizing ability of the gas and the temperature of the furnace in principle, though we didn't control that. And then how do we know that the copper is in the 1+ charge state? Well, we need to have an experiment that monitors the charge state. And for this, we took it to the synchrotron and we measured Zane spectrum. And the X-ray absorption near edge spectrum is very sensitive to the charge state. And then we want to autonomate it. So we need to have, I'll go into detail about how we do the automation part below. So this is the initialization part of this whole process. Now I'm going to go around how we did this closed loop part, the automation part. So firstly, you're going to set the experimental parameters. And so you have actually a machine that can do that, but it's under computer control. Then you initiate the experiment, all the parameters are set, and you hit the go button. And then when the experiment's finished, you measure the result. In this case, it's a Zane spectrum. You assess the result, and in this case, what we did is we had these example Zane spectra from different charge state coppers, and we took linear combinations of them to compare them to the measured result. And then you feed that back into some kind of algorithm that makes a decision whether or not to have the next experiment. So did you reach your target or not? And then once you decide you want to go again round the loop, then you have to have an algorithm that decides on the new parameters. So this is a kind of concrete example simply of how this loop goes, so you can get a clear idea. And then finally, you assess the result, and this is the conclude part of that loop that Benji showed. And here we had a target of the n equals 1 for copper to the n plus, and we were actually reaching it fairly closely, but not exactly. And then we drew some conclusions. So this is basically the anatomy of an autonomous experiment at the beamline, at least at the stage where we're at now. So let me take a step back and actually start thinking about give ourselves a report card at the facilities and what's already in place and what needs to be done and how we're going to get there for running these experiments at a synchrotron. So the first one is setting the experimental parameters, and things are in good shape here. Firstly, in order to be able to set the experimental parameters, you have to have your hardware under computer control. But not only that, you have to have a software API, application programming interface, that allows a software program to control the hardware. So it's no good just having a GUI. You know, you have to actually be able to address the hardware directly from a software program. And everything that needs to be controlled has to be controllable. You can't have some things that you can't have any air gaps. And then you need to take care of safety. You need to make sure that everything is kind of properly engineered, so nothing is going to break or blow up or kill somebody So there's quite a lot of like upfront engineering to get things ready. But from the point of view of facilities, we're already in great shape because actually we're always doing experiments in hutches that we don't have good access to. And a lot of stuff is already automated, and it's already automated using tools that are, again, I move my Zoom junk around. It's using tools that already have APIs. And so EPICS is a widely used tool at facilities, and this actually handles all of the different devices in a very heterogeneous environment. And taking inspiration from the software stack that they're using at Brookhaven, there's an OFID layer, and OFID provides Pythonic abstractions of the EPICS process variables. And so you could program directly in EPICS, but it's really, really nice to just have a Python layer where you can program on the front side of the Python, and the OFID layer will interpret what you've programmed, and then it will update the EPICS directly. So how are we doing? How's the how are the facilities doing? They're getting a passing grade on this. Then to initiate the experiment, this is again a software-hardware interface. You need to send a software command, and it can be done with a Python script, for example. But this raises a question that we would like to have a slightly more robust software infrastructure that's based on kind of asynchronous technologies and uses callbacks. This is a thing where you would like to be able to, for example, do something where you initiate a shutter open, but you could then wait some time and hope for the best. But a much better thing is that you then receive a signal from the shutter that it's actually fully opened. And then you move on to trigger the detector for some fixed length of time. And then you need to know when the detector's completed, and then you close the shutter and so on. And so having this kind of slightly more robust software infrastructure running the instrumentation using callbacks is really powerful. And again, this blue sky stack that they have at NSLS2, which is sitting on top of EPICS and OFID, is what it looks like. So there's definitely a green check here. But there's plenty of work to do. That not all the facilities have any kind of software stack that really looks like this. Even within Blue Sky, I'll show in a second that it's still under development for doing actually the feedback. Then we want to measure the result, and that means that your experiment is actually running in the hutch at the synchrotron, but you've received a signal from your experiment that it's ready to have it to be measured, and then you need to initiate a measurement. So this is again the same software-hardware interface, and we're going to use the whole Blue Sky OFID stack. But there's an additional issue here, is that we need to capture the data output from the measurement and be able to do something with it in an automated way. And so, a simple way to do it, and the way that we did it in at the APS, where we did our autonomous experiment with Karina's group, was simply monitor a directory, and then when a file gets written to the directory, then operate on the file. But again, having this more robust kind of software infrastructure, which is based on streaming and uses message passing and in this case, the event model. This means that you have well-defined data packets that are flowing through well-defined streams that you can subscribe to. So a stream of data is coming out of the instrument, and you can write a piece of software that subscribes to that stream, and then it can actually create and send a new stream back. So plenty of work needs to be done here. There's virtually no really robust data analysis, real-time data analysis software. It's being developed, but we're a little bit behind. This is what this Blue Sky stack looks like. So you have the hardware controlled by EPICS. There's this OFID layer I talked about, and then Blue Sky. So you write your scripts for running the experiment in Blue Sky. And then the output of the experiments is this stream, this data stream that goes into Kafka 0MQ message passing, message bus. And then it produces these streams that are shown by these arrows, and you can visualize the raw stream, you can send the raw stream to an analysis server and so on. And then in order to make the automation work, your analyzed data has to be then turned into an analyzed data stream that then has to be sent back to Blue Sky. So there has to be some logic in here that will actually do the decision on the updated experiment, and then these arrows have to go back through HOVID to EPICS to reset the experimentation. So this is maybe too much engineering. I don't know if you care to know about all this, but this is actually the challenge that we have to sort out, and we have to do it in a way that can handle a very diverse set of experiments that are very heterogeneous. And we're doing okay. We're doing okay. I think that we have a clear idea about how to get it done. So in terms of the assessment of the result, we need automated real-time data analysis. It could be just looking at a region of interest on a detector and counting. In Benji's case, in the early Aries experiment, he was looking at a Raman spectrum, I think it was, or some optical spectrum. But we need to like take information and often reduce it to a physics-based function and then fit models. And then finally, you need to have some kind of target function or cost function. And so that's basically saying how well your experiment has worked. And that's of course another human input place. That's where you have to really decide what your goal is, what your experimental goal, and how to get there. And then be careful what you wish for, because you could be optimizing your target function, but if it's the wrong target function, it'll be optimizing the wrong thing. So there's a lot of work going on in this area. There's something at SNS, the Neutron Data Integration Platform, I think it's called, and there's something at Los Alamos, this Mystic and Milk camera at Berkeley lab, and there's also stuff going on in the groups, our group and Gilad's group and so on. But we still need to do way better in this regard. This is an example of some kind of streaming software where you actually set up an analysis map, which looks like a directed graph, and you stream the data through it. And this is what's happening in my group, where you can actually then take data where you might have up to 40,000 frames here, and you're extracting different, we call them quantities of interest, which is any scalar quantity that you could actually be a vector, but that you can extract from your data by computation, and then you can make maps of it. So this is exactly the kind of thing that you need to do with this more streaming data reduction. The decision on the next experiment is just basically whether you've reached convergence. But there's some interesting ways that you can do that too, where you build in constraints. So you can have an experimental budget, for example. So in the case of beam time, it might be that given I have 2 days of beam time, what's the best use of that beam time budget to test my hypothesis? And in that case, the no-go decision that you don't do any more experiments is that you've reached the end of your beam time. But your cost function, the thing that you're optimizing, is how to make best use of the beam time before the end of the beam time. And mostly this is a fairly straightforward part of the whole process. And the more rich one is this one of deciding the new parameters. This is where AI can be used. You need a decision policy, which allows you to update parameters based on your prior experiments. The challenges here is that this decision policy has to be on the same time scale comparable to your experiment itself. So you can't have the decision policy as the bottleneck. It can be something very simple like a local optimizer, but as Benji said, most of the approaches use Bayesian inference, and this is because it maintains a memory of what came before, so it's making best use of this prior knowledge. You're basically trying to estimate a posterior probability distribution based on prior probability distribution and the result of the latest experiment. And you can put that in the loop so that the prior for the next experiment is the posterior from the previous experiment. So this is very, you often see this picture here. This is basically a picture coming from Kriging, which is a Gaussian process regression. And this is a commonly used algorithm if you're prospecting. It was actually developed in South Africa to do, I think, gold prospecting or something like that. But basically, it's like you've got a plot of land and and you're prospecting it for gold, and you have to dig these expensive holes. And what's the optimal way where you can find the most gold digging the least amount of holes? But that's even though this is a kind of fairly advanced for us, we're not used to using this in our everyday labs. There's actually a huge headroom for developing much more richer decision policies that including these knowledge gradient ones that Chris Reyes is doing with Warren Powell that Benji also mentioned. So there's a lot of work that can be done there that will lead to new things. But again, this is a different experiment that we did at NSLS2 to do basically grain mapping, and you want to actually, let's say that you want to kind of use the smallest. We did actually a grid search, which was very expensive. So we measured points on a grid for here. But all you're trying to do is do an image segmentation where you're trying to actually find the edges of your grain. You can do that in much fewer measurements if you use a Kriging algorithm. We didn't actually automate this experiment, but that would be an interesting thing to do. Okay, so just to close up then, what's some closing thoughts about automation? The human is not in the loop. That's the point of automation, but the human is driving it. It's really a human enterprise. And again, as Benji said, we want the machines to do the tasks that the machines do well, which are really tedious ones, or ones that are actually, machines are very good at moving around in high dimensional spaces, and human beings are very bad at it. We do something that I call slice and viz, where we take our high dimensional space and we make a 2D slice through it, and then we make a false color plot. This is how we do science right now, but this is really not the best way to make use of those high dimensions. So use the AI, use the machines to do the high dimensional stuff, but use human beings to derive novel insights, to synthesize ideas, and use their human intuition and their deep domain experience. And I want to make one last little plea that coming back to the data. There's this concept in data science of a fair database, which is findable, accessible, interoperable, and what's the R? I forgot. But
reusable.
Reusable, yeah. And this is a very powerful concept because we all save data, but it's very rarely fair. And what I want to say about when we do these autonomous experiments and we build automated data reduction, we want to actually save the data, but we want our analyses to be fast, interactive, reproducible, and iterable. And the reproducible one is really hard. So even in the domain of autonomous experimentation, we're not really talking about making it reproducible. Although you could run the experiment again using the same device, and it should run in the same way. To really make it reproducible, you would like somebody else with a different device to reproduce the scientific result. It has to be there has to be some concept of universality. And when we're thinking about this in terms of databases, we really want to be capturing, in my view, the data as the autonomous experiment happens. So if we have an experimenter who's doing the experiment in one lab and they're saving the results on their laptop, and then another one in another lab and another in another lab, we can't get any economies of scale. And if we are even using lab notebooks and writing them down in thousands of labs, we don't get these economies of scale. But if you have some kind of centralized data store and you have a structured way of saving it, and the data goes into there, you get enormous economies of scale, and you get these dramatic speed ups. And so we really need to think about it. So here's the Gartner hype cycle. Benji also mentioned this, so our talk's a little bit repetitive, but where are we with synchrotron autonomous experimentation? And I think we're probably about here. Like we're above the line where it's already starting to be useful, and it's being applied more and more, and our expectations for what it's going to provide are going to go off scale. Then we're going to go through this period when we're very disillusioned because we thought it was going to solve all our problems, but it only solves some of them. And then finally, it'll end up at this plateau of productivity, which is its real utility value. This is where we're headed, but we're really early on the journey, and it's an exciting time to be doing it. So yeah, let me just finish up and thank, as usual, all of the really great collaborators and students and postdocs, and the amazing facilities and the dedicated people who keep them running, and also the funders who fund them. So yeah, thanks very much, and happy to take questions.
Okay, thanks, Simon. Terrific talk. Very nice. So we definitely have some time here for questions before the break. Oh, sorry, before the next speaker. And so feel free to raise your hand or put something in the chat. And while we're waiting for that, I have one. So this is a bit kind of in the weeds here, but it's back to your proof of concept problem on this copper oxidation state. So if you started this, how were the initial conditions chosen? And if somehow or other different initial conditions were chosen, did you always get to the same endpoint? And did it take longer? Could you get there faster depending those states, or kind of what was the detail behind that?
Well, we might need Karina to help with this, but the initial state was actually copper 2+, so I guess CuO, and it was on a substrate, on a kind of it was finely powdered, or on a kind of on a substrate of that was porous that the gas could flow through. And some prior work was done by Karina's group to actually find the range of temperatures where this thing could operate. So this kind of raises some of the issues of how autonomous experimentation, it's like autonomous cars. They kind of work really well in the domain that in some kind of specified domain where they're supposed to operate. And then if you let them go outside of that domain, they're not very good at extrapolating. So there's still quite a lot of work up front of actually designing the experiment and deciding the temperature range, deciding the composition range. And then it's just doing an optimization within that parameter space. And then your question was how did we try different starting points? And I think the true answer to your question is that it took us a long time to get the whole thing going. And then we only got our data in the last kind of 10 minutes of the beam time.
Right. So a standard kind of beam time experiment.
Standard kind of beam time experiment. Yeah.
Great. Okay. Other questions or comments? Yeah. Suchi.
Hi, very nice talk, Simon. I'm just wondering, you got opportunity to work with blue sky automation. Have you ever worked with the spec? And if you are, then what are the differences and what exactly you find interesting in blue sky?
So we have worked with spec, and many years ago we worked with spec. I haven't worked with it for a while. The experiment that we did at APS, I think, was running with spec, actually doing the instrument control. But blue sky is basically designed to do this automation. So I think that what I would say is that there's a rather huge learning curve if you're starting to interact with blue sky. It's a completely different language that we're not used to, and it's based on something coming from computer science, which is basically asynchronous callbacks. And this is coming from kind of parallel computing, where you can have different processes going on, and then you can have process A and then process B, and process A has to wait for process B to finish, and then once process B is finished, then process A can do the next step. And so the whole thing is kind of designed to allow this to work. And it has this other characteristic that it can do things in a streaming fashion, so that you can start your data analysis before the experiment has ended. And so just from a kind of a computational engineering point of view, it's a much more robust and scalable way of doing things. You can have your analysis programs running on different computers, even remote computers. If your data analysis process crashes, it doesn't crash your data acquisition, things like this. So I understand it's actually very difficult for people to get their head around using Blue Sky, but it's a gift that I believe personally that it's a gift that will keep on giving.
Okay. I don't see any other questions. So again, we'll have more time for a conversation at the end of the day. So
hello.
Oh, I'm sorry.
I raised my hand.
I apologize. That's right up there.
Okay. Sorry. I think there are some points that cross my mind, especially when it comes to data and data analysis, because what you're saying with Blue Sky, where I see advantages of Blue Sky, which might be of high importance, especially for autonomous experiments, is to combine the data from various multimodal approaches, right? Because that's the weakness of SPEC right now. For SPEC, it's incredibly hard to synchronize two different computers and how to merge the data at the end. And I think that's the opportunity what you have as Blue Sky to have this real timing of various probes and to make sure like that the timestamp is identical, right? And also how to cure the data so that they're really ordered in a way that it comes together. Is this correct?
Yeah, this is correct. So when you set up your experiment, you have it's usually more than one experiment, and those different and the things have different timescales. So you might be triggering your detector 10 times a second, and you're changing your temperature once every 3 minutes, and you're doing all these things with different timescales. And what it allows you to do is to synchronize all these different components.
There could be also a secondary detector, like a Raman detector, which takes a minute to take a data while the X-rays are coming in fractions of seconds, right?
Right. So it's extremely, it was basic. And I think one of the huge challenges at synchrotrons and in experiments in general, like, I mean, something where automation was always going to work well was on a production line where it's doing the exact same thing every day for days and weeks and months, right? And it's easy to see how you can just bolt automation on top of that so that the thing can actually make small adjustments, but it's still basically doing the same job. But at a synchrotron, your instrument scientists say no, like one user is doing something and then the next user is doing something completely different. So you need to engineer the hardware part of your beamline that allows people to snap their new experiment into the old one and everything is in the right place and so on. But you also need that same kind of properly engineered capability for the software, so that I can write if every experiment looks the same, like in a kind of a tomographic imaging case, for example, like every experiment is the same, I can engineer the software very easily. But if I have this situation where every experiment is different, I need something a little bit complicated like Blue Sky.
Yeah. I could expand here, but I think we are running out of time.
Yeah.
Is this correct?
Yeah, I think we better get going here. Sorry, Ute. Again, you can pick up in the end. Okay, so thanks, Simon. That was terrific. And our next speaker, and the third in this session, is Chris Tassoni from Slack. And so we've turned from sort of a very broad view to sort of some nuts and bolts stuff at the synchrotrons. And now Chris is going to tell us about a very important problem in chemistry and how artificial intelligence is going to help us discover novel catalysts. So Chris, take it away.
Perfect. Yeah, and I'll actually probably end up focusing a little bit. I tweaked my talk in real time to focus kind of more on the facility perspective a little bit, but with some specifics. I would note, just to to throw in my 2 cents on the end of this, all the work that I'm going to show here, which is completely closed loop autonomous experimentation, is actually built on spec as the operating system for the Beamline. But it is 100% true that you need some other multi-thread layer on top of that, right? So we built our own Python layer, but there's other ways to do it. So coming from SSRL, which is where I work, we have a huge focus in our materials division on developing in situ and operando sample environments across a large range of applications, right? So these are all the way from things like molecular beam epitaxy to metal additive manufacturing. And exactly the point that Simon made is 100% true. Our beamlines are set up to be able to accommodate this like vast array of different types of sample environments. And so that's really the perspective that we tend to think in terms of incorporating machine learning and automation into our program, is how can we do that across these diverse sets of tools? And that can include tools that are really looking at material fabrication, but also systems that are looking at materials or chemistry in action, where the space that you're trying to design experiments in is changing a little bit. And so just really briefly, my research group, I wear 2 hats here. I run my own research group, and I also am the division director for the material science division here at SSRL. And we tend to think about how we can combine in situ experimentation, autonomous data analysis, and active learning strategies for design of experiments in a few application spaces, primarily catalysis, photovoltaics, and additive manufacturing. And so really, when we think about what our standard user experiment looks like, whether that be my research group or any external user research group, you start with some plan for what your data is going to look like. You come here and you collect some amount of data, whether you have a day, 2 or 3 days, or whatever. You're going to go, maybe while you're running your experiments, do some first pass analysis. And so that's like the near real time. Usually that's designed to assess, did I collect reasonable enough data so that if I go home, I won't be severely disappointed that I collected garbage. But then the real work begins, and you start analyzing and interpreting your data, and this can take many-fold longer in time than it took to acquire the data. And then you're going to contextualize that information in what the hypothesis that you're generating to try to come up with your next set of experiments that you want to run a few months later. And so our objective throughout all of the efforts that we've had for the past several years has been, how do we make this a near real-time loop? And so I think both the first 2 speakers talked about this in great detail. But I think one of the unique things at the facilities is, again, not to belabor the point, but that you have to do this across really different types of experiments. The one that I'm going to use to motivate the talk today is basically, if we want to make a transition to a sustainable chemicals industry, we need to move away from fossils as a feedstock into either post-consumer waste like plastics, agricultural byproducts, or hydrogen and CO2. And what this really means is that you need to re-optimize this entire chemicals manufacturing network, which is a beautiful example of a very highly optimized network of chemical reactions where any byproduct from one reaction is being fed into another. And what this means is you can't muck with one part of this without potentially changing another component of the reaction. And so you really need to think across the entire reaction network. And we need to redesign all of it because it generally has petroleum as its, or natural gas as its feedstock source. And we have the further constraint that if we want to do this with anthropomorphic carbon as our motivation, we largely have to use the infrastructure that's in place, meaning we can't build new types of chemical plants without having a huge expenditure in carbon. And so we need to find a way to use the existing complex. And so that's essentially a design constraint. The dream scenario, and what we've been trying to work towards for quite a long time, is an integrated platform that's going to predict catalyst activity, selectivity, and lifetime across a huge range of reactions. And you would want to feed this with all different types of data and able to do that. We've spent the last 6 years really working on how we can do this AI-driven synthesis component, and only recently are starting to work on AI target prediction, I would say, beyond typical theoretical inverse design. And the reason why we're interested in this AI target prediction is that if you want to design, well, I would hypothesize that if you want to start to train AIs to predict the activity and selectivity and lifetime of heterogeneous catalysts, you're going to be able to do that with a much smaller quantity of data if you have well-defined catalytic systems where there are clear descriptors between the structure of the catalyst and the activity and selectivity. And so we've been working for the last several years with Matteo Carniello's group down on campus at Stanford. And what they do is they make well-defined libraries of colloidally synthesized metal nanoparticles. And then they put those on different support materials and use those to look at reactivity trends as a function of the composition of the nanocrystal. And the key thing to point out here is when we talk about well-defined metal nanoparticles, these are sub 10% standard deviation. And at these sizes, that really means you have essentially, you're only varying within one lattice parameter of the underlying metal. And so there's a really homogeneous systems, which helps to understand the reactivity trends. Sorry, I need to move something. But for anyone who's ever done any colloidal synthesis, this process is very labor intensive. So again, to the points that have been made previously, typically you're mixing up some solution, you're running a reaction in some kind of batch fashion, you're recovering your product, and then typically you're using electron microscopy to ask if I made what I wanted, yes or no. Almost always the answer is no, and you start this loop back over. When the answer is yes, you have a few additional processing steps before you can measure the activity and selectivity. And so in order to make what I'm showing here is a histogram, set of histograms from electron microscopy of a library of, I believe it's 12 nanoparticles that are attempting to have 1 nanometer steps in size, that were made. These, in this case, I think this is palladium. And this library is used to study several different reactions, including CO2 combustion and others. But this library took a very talented third-year grad student a year to make. And so this is right now our slow step in this kind of discovery loop that we're interested in optimizing. And so we wanted to ask ourselves if we thought there was a way that we could do this in a closed loop autonomous fashion. And the steps that we need is we need to have a synthesis recipe that's created and sent to some machine controllable system. Those conditions get sent to a machine controllable reactor. We need to measure the structure as a function of the synthesis condition. We need to be able to interpret that measurement to get the information that we care about. In this case, that's the phase of the nanocrystal system, the size, the shape, and the polydispersity. We need to package back up or stream into a database the information about the recipe and the outcome of the data interpretation. And then we need to have some type of decision-making algorithm that is deciding what the next recipe to try out is. So I'm going to kind of walk through how we solve for these different steps here, and to start with measuring the structural evolution. So the first step that we took was, when you have a synchrotron outside of your office, you try to find ways to use it. So we have a simultaneous small and wide angle X-ray scattering beamline that can work at high enough energy that we can get through either a batch reactor like the one shown here, or a flow reactor like one I'll show in a little bit. And small angle scattering gives us all of the information that we're most interested about the particle. It can discriminate between the shapes of different nanoparticles, the sizes of different nanoparticles. So the red trace here is a 2 nanometer particle, the blue trace here is a 10 nanometer particle, and the polydispersity of different nanoparticles. You can see the damping of these oscillations as you increase the polydispersity. And wide angle X-ray scattering can tell us about the composition, essentially what's the phase of our nanocrystal that we're interested in. And we can, sorry, I'm actually going to skip that slide. The challenge, though, is that it's generally very labor intensive and takes experts to be able to go from the data that I just showed you to the parameters that you actually care about. And so the initial scope of this project was a 3-year project that was funded by the Advanced Manufacturing Office. And 2 of those years were solely focused on how to automate the data interpretation. And what that challenge really looks like is when we run these types of autonomous searches, we start from 2D data that looks like this in an image stack. We need to perform a bunch of routine operations, and this is all really easy to automate. But then we need to fit the data to some model that is going to tell us about the size, shape, phase, polydispersity, and number density of nanocrystals that we have. And this is not something that is easy to do using heuristic approaches. And then ultimately, as Simon pointed out, we need to aggregate the tag data in some kind of way, and then build models for extraction. And so the flow looks like that is shown up on top. We're essentially taking a 2000 by 2000 dimensional array, integrating it down to some smaller representation of the data, but ultimately we just want to end up with a vector that's maybe 4 or 5 dimensions long. And so the other kind of point to make is the approach that we took when we started this project was, I run a group that does a lot of small angle X-ray scattering. We were just going to use hand-labeled data, so data my group had fit for the various projects to train the algorithms to predict the fit parameters for the data. And so when we looked across what we had maybe a couple of thousand small angle scattering patterns that were fit. And that is not a large amount of data, especially if our input dimensional space is a 1000 by 1000 array of a pixel camera. And it isn't really enough data actually to even just use the one-dimensional data as the input. And so we needed a way basically to go through a feature engineering exercise where we can reduce a small angle X-ray scattering pattern, so that's the black curve shown here, into a set of a much smaller number of scalar descriptors that we think capture the important metrics of the data. And so what that exercise, and then we want to use a set of machine learning models to basically predict the fit input parameters from the smaller, I think it ends up being a 28-dimensional input array. So what this looked like in practice was a large feature engineering exercise where we simulated a much larger amount of data than we had access to. So we treated that as ground truth. We came up with, I think, 50 parameters that we thought describe the simulated data. So these are anything from extrapolating the I0 intensity, so extrapolating the intensity to 0, to trying to locate the fringes, the oscillatory fringes in the data, to a whole bunch of other much more difficult to describe mathematical descriptors. We took those, fit them to all the simulated data, mapped those into new latent spaces to see if we thought they were separable. And then when we found parameters that we liked, so that we thought we could separate out with something like a logistic regression, we then tested whether or not we could locate these parameters on actual data, which turns out to be the hardest part, because this also needs to be able to happen in very, very fast timescales. So in this case, we're acquiring a scattering pattern every couple of seconds. This parameter locator needs to work in millisecond timescales or faster. And then ultimately, we took this set of features that we felt describe the data and use them to train a set of machine learning models that then predict the fit parameters and then finish with the least squares minimization. So in practice, this code is available in this GitHub repository. I would note we use the most primitive machine learning models possible because we have small data. And what the architecture of our interpretation pipeline actually looked like is we have a set of curated data sets that are essentially grouped together based on the number of scattering populations that are present in the data. Because of course, when you're doing a material search for new materials, the least common thing you will see are high quality materials that you synthesized. And so you need a way to be able to interpret really messy systems. And so in this case, we are very commonly synthesizing either really inhomogeneous populations of nanoparticles or bimodal distributions or things that would form superlattices spontaneously. And you need to be able to interpret data that is mixtures of all of those phases. And so what this first classification layer is just classifying like data with like data. So similar numbers of scattering populations. And then from that, you end up running another classifier on these different systems that is trying to classify essentially which form factors you should have describing your system. And then lastly, that initiates a pipeline that feeds several sets of regression algorithms, which predict the radius, polydispersity, number density of nanocrystals. And then that feeds the least squares minimization. And so when we do that, this is the confusion matrix for the labels for the types of scattering systems in terms of classifying them that we used for this particular set of experiments. We end up being really good at classifying and solving all the regressors for the population we most care about, which is well-defined dispersed nanocrystals in solution. We also do a fairly good job of classifying materials which don't fully react, which is this pattern over here on the leftmost side, as well as materials which form phase pure superlattices in solution. But we do a really bad job. This one on the right is essentially these lower populations where we have a superlattice and dispersed nanocrystals and a second superlattice all coexisting in solution. And so there becomes a threshold in terms of the phase purity that we simply can't handle, which turned out to be okay because we don't want to make materials like this. And so this ends up being easy, as I'll talk about in a second, in the design layer to filter out. I'm going to go a little bit faster because I think I'm running long. So just to diverge for 1 second, we spent a huge amount of time going through this feature engineering exercise because we wanted to use hand-labeled experimental data as our ground truth to train our algorithms. A couple of years later, we were working on doing something similar for powder X-ray diffraction, and I had a grad student that came to me and he said, "That is stupid. We should just use a convolutional neural network and take the powder diffraction pattern as the input and predict the lattice parameters as the output." And I was adamant. There have been a number of papers that showed if we train on simulated data, it simply doesn't work. And he said, "Let me just try." And so he went and mined the data in all the crystallographic structural databases, which is close to about 1 million SIF files and powder X-ray diffraction patterns. This is what the representation from the 3 databases that we pulled from looks like. And then we looked at how we can start to account for non-idealities. So this is just an example for the cubic system and a triclinic set of subsystems. We're showing the mean percentage error, and as a function of what we included in terms of data augmentation. And so in the perfect case where we have perfectly simulated data, the algorithm does fairly well with about a 7% mean percentage error, and slightly less than that in the case of the triclinic. And it doesn't particularly care about 0 error offsets or intensity modulations in the spectrum. And in the case of the cubic, it doesn't really care about even broadening the peaks, but obviously this matters for the triclinic because you actually lose a bunch of the higher order peaks that you care about. But it did, I think each of the algorithms cared a lot about changing baseline noise, accounting for that, and then the inclusion of multiple phases, which is not too surprising. But it turns out if you are clever with your data augmentation strategy, so I think here it probably only matters to compare this box, which is taking a model which is not trained on the noise that we're talking about, noise augmentation that we talked about, and then being evaluated against data which has that in it. The systems do horrible when you don't include augment the data to account for these noise, and you can, in the MM is trained on modified data and tested on modified data. You recover the performance of essentially the perfect model in most of these cases. And so this is all to say that, and then this ends up actually working on experimental data fairly well. So to say that there is, I think, totally pathways to using simulated data sets. You just need to account for the actual non-idealities you experience in the instrument. So let's see, I think I have like 3 minutes left. Just take a minute to say, it actually, I think, in my opinion, Simon talked about the active learning strategy is the easy part. So you can use just a simple Bayesian optimizations for most of these types of experiments. You just need to parameterize the input, which in our case was the sets of flow rates, the temperature, the relative fraction of the various reagents, and then the set of outputs that you care about. You also need to be able to build machine controllable hardware. So this is what our flow reactor looks like, where we have a set of pumps, temperature control system. This is all controlled by a set of Python modules we wrote, and then the beamline, which we interface through another set of Python modules. And in practice, what we are doing is, when we're using Bayesian optimization, is to fit some objective function. In our case, we use Gaussian process for this. And then the BO is providing an acquisition function, and we're trying to search this space as efficiently as possible. It turns out, in our case, what we did is run a random grid search of 18 experiments, and then we turn the active learning algorithm on, and we're able to hit the target size nanocrystal we want in about 36 total experiments, or 28 additional iterations. Generally, you don't want to just synthesize one material, and you'd like to synthesize many materials. And so another strategy to do this is set up a bunch of models in parallel that you're going to query. In this case, we have 8 different targets that we're running that batch of experiments, retraining the model, and then querying it for new sets of experiments. And we can identify all the synthesizable materials given this chemical composition that we had access to within 3 target iterations using a Gaussian process with Bayesian optimization. This has tons of benefits enabled in terms of generating large amounts of data that then you can identify heuristic design rules that define the relationship between the inputs and outputs. And then you can test different sampling strategies in order to understand which active learning algorithms would have been the best had you employed them. And where we're spending a lot of effort these days is trying, I think I agree with Simon completely, in that we have a lot of room to move beyond just standard Bayesian optimization. And so this is an active learning set of active learning strategies BACS that was written by one of Stefano Erman's graduate students, Willie Niegelmeiser. And in this case, what you're seeing on the right is essentially a comparison in terms of the number of points you would have wanted to hit, which is we wanted to identify nanoparticles below a certain polydispersity, but in certain size bins. The blue is just maximum uncertainty sampling. Black is posterior mean uncertainty sampling, and green is the algorithm that we're currently using, BACS, and you can see that we can get to hitting maximizing the number of real targets much more quickly. So I'll probably stop there for questions, and maybe just ending with the thought that I've shown an example of how we actually close this loop down. But the key to impact user science and bring about all the democratization and everything we're talking about is you want these methods to be available for like 90% of your user community. There's always going to be outlier experiments, but how do we bring these types of tools to the most number of people? And then that allows us to potentially create more homogeneous data sets across user groups that we can use to drive the algorithm development component. And so these are things I think that we're more interested in as we move forward. But in the early days, I think it was important to show that this is possible, which is what the goal of this project was. So thank you so much.
Great, thank you very much, Chris. Very nice. Questions from anyone? Raise your hand, put it in the chat. Okay, let me start then. So I have one, which again is a little bit in the weeds, and maybe I missed something, but it seemed like when you were discussing this sort of data modeling, so the idea was you had all these complicated data and you were trying to map it onto some finite number, like 15 or 20 parameters, and the sense is that could be to describe the data, and then that could be then in some way translated into sort of physical parameters. And my question is, do you have any basis for like understanding that like a unique sort of a one-to-one mapping between these things, or what's for that linear transformation, how do you know that it's invertible, I guess is my question.
I would say I don't know. So we're using logistic regression for the classifiers here for that. And then linear regression. So I don't know that it is invertible, but I do know the exercise we went through in terms of feature engineering was essentially to evaluate the predictive power. So we have that confusion matrix shown and F1 scores, et cetera, as a function of leaving various parameters out, retraining the model, and then evaluating its predictive power. And so the features that we left in, I think there was initially a total of 54 features that we had thought would be important. And this was a mixture of things that we knew mathematically we could get out of the data, and then things that talking to various experts, what they look for in the data to try to guess at fit parameters, right? So I think you always have this thing, especially with people at facilities who can walk by an experiment and say like, oh, you're looking at this material, right? And the question is like, what were your cues? And so that's what we tried to build in. But to be totally honest, by the time we had the autonomous data interpretation working, we needed to immediately go to the beamline. So a lot of this we were fixing in real time as we were going about it. Since then, we've used this across like so I can't really answer your question because we didn't test it all of that much in terms of the invertibility. But I don't think we could define a functional form which relates those 20 parameters to the output parameters, right? So this is getting fed into like a black box, right?
Good. Uta?
I was a little bit stumbling over your bold thesis that you would like to have 80% of the experiment using autonomous experiments algorithms.
So I think, and I probably said that poorly because I knew I was running over time. What I mean to say is, myself included, there's been a lot of effort of people building like one-off demonstrations of these types of things. And what would, I think, be the most impactful things we could be doing are building the tools that maybe are not as like flashy as an autonomous reactor, but that would impact the largest fraction of our user communities, right? So that might be something as straightforward as mail-in powder diffraction that's run by a robot, which many of our facilities have. Yes. How do we optimize the instrument condition in real time based on feedback of the sample, right? And that's going to impact a huge number of users versus the community of people who want to synthesize things at beamlines and let the ML algorithm figure out how to synthesize it small.
I don't see such a big opportunity for ex situ samples in mail-in, because there you can use mathematical algorithm to optimize it pretty fast and pretty well. But of course, if you also think about mail-in and do some in situ work, simple in situ work like temperature dependencies, which is possible, then of course I see clearly like the advantages here to also expand on AI algorithm. I have a question. It was much more related again, like thinking about me and the diversity of experiments what we have My group has started to work on auto-masking issues, because this is one of the biggest obstacles here in the way, right? Because as soon you have something like working really in situ operando, sometimes you have features coming in which are a clear hazard to any kind of auto integration. You should be super careful with it.
Mhm.
Did you also think about it, like how to cure the data to prepare them for first integration before you go ahead? So to look for example, single crystalline spots from the sample environment suddenly moving in, something like this.
So but there's the standard set of data cleaning steps you would apply to any 2D scattering image that are happening before we do the integration. The short answer is no. The slightly longer answer is we prepare the data identically to how we would if a human were interpreting it. And then one of the advantages of actually training our interpretation algorithms on the data on the same exact system on the same exact instrument, right? So those types of non-idealities that would show up in the data are present in the training data. So I think that does result in more accuracy, but it decreases the transferability of our algorithms anywhere else. And it also is insanely labor intensive, right? Like the way that we tried to mitigate this was that program XRSD kit, it's basically just a Sachs fitting program, right? And so our initial thought was we built a standalone program. As you fit data, there's an ML algorithm learning in the background. And so it's going to start to get really good for each client. Will have their own algorithm that's on self-similar data, and it'll predict everything. It turns out, in shock to no one wants to change their analysis program, right? Like, even if that is a major benefit, my group uses XYZ software, and that's just what we do, right? And so that was a hurdle.
Yeah, I think I can't see so much the same here. I mean, I think people were trustful for the beamline scientists. I know that we are running already into the break, but I would like to catch on again on a thought, because it's something I would like to find answers here in this workshop, to be fair. One is again like about, for me, for data quality. I mean, I don't want to show up here somebody who is pushing back on autonomous perfection. Not at all. I mean, otherwise I wouldn't contribute to such a workshop, right? So it's something like I'm really completely dedicated to it and into it. But of course, I have also worries, because sometimes, like, coming back again and again and again to data quality and so on, it's really something like we are getting better at training machines, but when do we train our next generation scientists? Because we don't do something completely different, right? But the reason why the experience is just coming to a beamline, look over the shoulder and say, oh, that's this. It's like, where's it coming from? Or like, well, you have problems with your slit. I mean, there's obviously slit scattering in there. Do something about it. So that's something, because I have years of experience looking at this data, right? So that's the same. The question, at least, it's again, like, I don't think it's in the way. It's just something we have to consider and keep in mind how we want to do it. So it's not controversy, you know. It's just something where we have a common development, like how to ensure these data checks and qualities.
One thing I'd throw out, right, is like, almost as a consequence of doing these autonomous types of experiments, we'll have the ability to train, essentially create digital twins of our instruments. And so that, as a teaching tool, I think is incredibly powerful to accomplish what you're talking about, right?
Okay.
In the same way that, like, you know, once upon a time when I was learning about scattering, I spent a huge amount of time just simulating different scattering patterns and trying to understand what the impact of changing different parameters was going to be on the endpoint. And then you go to your first beam time and you realize, like, no data looks like my simulated data. But you at least have that foundational information to start to figure out, like, okay, my peaks are shifting in this way, that probably means this. So if we are able to create really representative twins of our system so that people can run virtual measurements and start to develop that intuition, right? I think that just becomes part of essentially how we have to train people.
Yeah.
But
yes.
the point that Simon made, I think, is really key, right? Almost all of our work now is on how do we structure the acquisition functions to ask materials questions, right? And so like that's where I'm seeing this new generation come up, is really interested in like, I don't want to just optimize a single, like I want to understand opportunity cost and how to build that into my algorithm and all of these types of asking really more complicated questions and then trying to put that in an algorithmic framework that makes it easy to programmatically ask. Right. And so I think that's an interesting frontier that will train a whole, scientists who think way differently than I do.
Yeah.
Okay, Simon, you had a quick one?
Yeah, just on this point of Uta's, I mean, I think developing the next generation of beamline scientists who know all the hardware and stuff is a different issue, but training the users, because in principle we're making the experiments much less costly. So you can be sitting at home and actually running the instrument. It's actually somehow easier to train, and you can train an AI to make a tutorial which has bad slits, has the slits set badly, and you don't tell the person. So I agree with the digital twin, but that's a heavy lift. We tried to do that for the XPD instruments, and my group turned into like 100% just working on this digital twin, which wasn't going to result in a Nature paper or indeed any paper. But you can also, because the cost of the experiments is much lower, you can actually allow people to run the machine, and you can actually put little roadblocks in their way and have them solve it. It uses up some of your beam time, but because the experiments are cheaper, it's something.
It's a little bit more to it. I don't want to diminish it so much. And actually to the other ones, I'm running into the break here. I would like to keep at least 10 minutes of the break, but I would like to keep up that we restart at 3:15.
Okay. So we are running behind, but that's either the measure of a lousy chair or very engaging speakers. And I think
it's okay. So, I just wanted to give people a chance to understand like that we are running into the break. But Simon, I didn't want to stop this discussion here. So this is something like it's not just slits or whatever. So it's really also a deeper understanding of data, right? Because to have slit in the beam, it's one, but also to see like, wow, if you have something like this, your whole integration won't work. It won't work, right? And that's something like I agree with Chris. I think we can develop training programs that people understand this better, and also to figure out like, is it the feature like we want to kill because like we want to just mask it out because we are not interested in this, or is there actually data in there? So to have still this moment of like, oh wow, maybe it's not a bug, maybe it's a feature, maybe it's something really interesting, we should dig for it. So these are these decision makings, and again, like it's nothing against autonomous deflection. I don't want to show up like here as the enemy to it at all. I mean, I'm really embracing it, but I'm just wondering like if we are sharp enough on the obstacles to be aware, like to really be prepared and also develop other tools as well. I mean, how to flag data to say like, you should better look twice here. So that's much more the point, right? Also, my nightmare is always like some people, they take our quick analysis, what we do on the flight with simple algorithms, they take it as the real data, right? So they never look again on the 2D data. A complete nightmare for me, because it's something like where it means like you trust the data immediately, completely. You know what I mean?
Yeah, no, I agree with that. Like I was kind of a big fan of streaming for a while. Like, oh, streaming is going to be brilliant. We'll do autonomous experiments. And then my students are like, well, we stream the data and then they get the data home and they want to like reanalyze it 25 times in batch mode because the stream data didn't, there was a shadow on a detector and this and that.
Yes.
So
Yes.
we need a parallel. So I advocate a parallel development, like really
Mm-hmm.
good
Yes.
batch processing stuff
Yes.
that you can rerun experiments.
Yes.
Like, yeah.
Yes. Yeah.
I agree.
We agree. We agree. We agree. It's just like so that's what I meant with parallel development, right? So like to be concerned about the problems we have, that we're not blind to it, not a blind selling like this is all wonderful and great, but to stay on the tip of our toes, that we also develop other things at the same time and also advocate for it, right? So I'm completely with you, because the on-the-flight analysis is very important, and to 90% it's okay, right? And of course it's always a key also for the autonomous experiments to be very fast on it, but to keep the awareness, there's also alternative truth behind it. Okay,
Right.
I need a short break.
So I'm going to suggest that we give a 15-minute break here and come back at 3:20. So let's do 15 minutes, okay?
Okay.
And I guess we'll start, and Uto will be the chairperson for the second half of this afternoon. So okay, we'll see everybody in 15 minutes.
I put it in the chat.
something really interesting. I will go through the process where we did autonomous closed loop material discovery and gave my view on the current challenges and summary of the talk itself. So as you know, there are more than hundreds of elements in the periodic table, and even you consider the 25 intoxic, inexpensive material, there are several possibilities to find these alloys from large complex compositional space. So the challenge here is how quickly you find the right alloy in this fast group of alloys. So even you can do the high throughput experimentation, it's going to take decades to complete the search. Therefore, you need certain kind of guidance. So in this talk, I'm going to talk about the strategies, how we actually develop the alloys, designing the alloys. So historically, domain experts' knowledge and the theoretical laws predominantly plays a critical role for material selection of synthesis, characterization, and property measurements. However, this process is really expensive and time-consuming. Therefore, a lot more effort has been given towards the different computational methods, whether it's DFT, MD, or others. Here, the challenge is local heterogeneity and defects become more and more common and critical to stabilizing the metastable structure. And it's become computationally expensive and slow when it comes to computing the ground state of the solid solution for multiple element system. In addition, it's not able to take care of the different synthesis procedures as well. Therefore, we started looking at the data-driven machine learning. So in early 1995, there are initial research published and talk about the machine learning material property optimization. However, the true revolutionary work happened when the material genome initiative started, and everyone knows about that. So I'm going to show how we proceed to the approach. So material design is a problem where the goal is to maximize or minimize the desired property of the materials by varying certain features. So we started with creating our own databases, then create the model. It could be feature-based, featureless, or physics-informed model. And finally, we choose our best model to the Bayesian optimization, and then do the synthesis, structural characterization, and property measurement. In this case, we do not throw the results. We iteratively put the results to the data sets and improve our model. So here I'm going to give two examples. One is for thermoelectric materials, where we implemented the physics-based machine learning model. The second example, I'm going to talk about the metallic glasses, where we discovered exceptionally hard and wear resistance metallic glass. So for the data, here is the thermoelectric material. So as you know, the world demand for the energy is increasing, and fossil fuel become really alarming due to the global climate change. One way to improve the sustainability of this material is going towards the complex compositional space. So here you can see there is a hot channel and there is a cold channel. So what I wanted to really do is creating the charge higher and lower the gate. So the best thermoelectrics here are those semiconductors that are so heavily doped that their transport property resembles like a metal. So one way to do that is lowering the heat and improving the transport property by going towards complex compositional space by solid solution, and manipulate the configuration and entropy of the material by introducing the new species, because it can create the lot of strain and increases the Sponon scattering by creating the disordered and distorted lattice. So my objective here is to design the low lattice thermal conductivity material in a higher dimensional space. But what exactly the space I'm referring to? So if you look at this diagram, you can see the yellow, what I know so far. There is a vast unexplored region where I don't know where my desired material will be. So we thought, does the model actually help us to reduce this unknown search space? So the very first thing, we turned to the model. So we started with the physics model at the very beginning. So usually the physics-based model typically encode the knowledge in the form of conservation and constitution of law. And this theoretical development happened with the validation of experiment, right? And it sometimes developed over the decades of knowledge, if not centuries. So here, one of the models which is really popular is called Clemens model. What it does is basically taking care of the doping or alloying. And it's important to understand this impact of the impurities with the point defects perspective. So here you can see the radius, mass, and the potential energy distribution, and Clemens model based on these three parameters. So very first analytical 5-dimensional space model we developed and very recently published in Advanced Electronics Material. So if you look at here, in the vanadium iron antimony and tantalum iron antimony line, there is a low lattice thermal conductivity. However, when we put the experimental results, we do find this is the region where the experimental results works really well. However, if you look at here, the theories does not actually capture the model complexity because there is a large mass difference between the vanadium and tantalum. As a result of that, the model tried to oversimplify the phenomena. So the theories does not capture the complex phenomena. At the same time, it completely ignores the uncertainty of the predicted model. So we turned to data and the model and thought, does the model plus data can help us to better understanding the search space? So in the data-driven model, we know the data is expensive and sparse and often no data in the desired spaces. So is it possible to explore the unexplored spaces when you have no data at all? We turn to two things. First is the global model. In the global model, we did the feature-based machine learning. And then after getting the initial guidance, we did the local model by Gaussian process regression. So in the global model, we are using the MatMiner. MatMiner is a Python-based package developed by Dr. Logan Wood. MatMiner facilitated the data-driven methods for analyzing and predicting the material properties. So Logan approach is to transfer the composition into desired features. So MatMiner works like a chemist. If you have a potassium bromide based on the knowledge of sodium chloride, it can give some idea of what would be the potassium bromide properties will be. So MatMiner have those transformed raw data compositions and properties to a meaningful feature. So feature extraction is actually comes after the database cleaning, and I'm working with the 800 data sets. So in this feature engineering, after doing the feature engineering, we do the random forest building and then do the validation with k-fold cross-validation and the predictions. So if you look at the scatter plot here and compare the ML predicted lattice thermal conductivity data against the experimental data, we find the mean absolute error 1.07. And we do find the coefficient of determinant 0.75. It means 1/3 of the data actually can be explained by the model. The success of the regression is based on ability to capture its relative variation of the property as a function of features. So if you look at here, our global model gave us some predictive window. However, our data and the model inherently comes with the uncertainty. The advantage of the operation of the research and machine learning suggests that merely choosing the prediction out of regression is not the best way to select the composition with the predicted values, because our data sets is relevantly smaller and our data definitely have uncertainty. So we do not only get the prediction, but also the uncertainty of the material itself. So after initial guidance from the MatMiner, we explored the local region by the Gaussian process regression. Just to give you an idea of what Gaussian process is a local model. It's basically give you the non-parametric and probabilistic model. Also, it's a non-linear relationship. So non-parametric means as GP does not rely on the parametric assumption. Instead, GP is flexible and is capable to adapt the model complexity as more data arrives. So certain advantages of the GP is you can actually improve or get your knowledge in the basis of kernel or the mean function inside the Gaussian process regression. So I'm using GPCamp developed by Marcus, who is in Canada. And this is what our 5-dimensional model looks like for the first generation Gaussian process. So here I am working on only 7 data points in a vast region. And this is what the first generation model. However, it did not give me enough information what to do next. Therefore, we turn to the global model and take the prediction and uncertainty and actually synthesize the bulk sample by ball milling, arc melting, hot pressing, and annealing, and get 7 more extra data point. So after getting the first generation model, we include these new experimental results and got our second generation model. What about the uncertainty? So as we know, because we added more data point, uncertainty goes down significantly. So here you can see leave out 1 cross-validation shows 14, here 9.232. At the same time, it also lowered the average uncertainty of the model. Now, if I look my search space, there are still a lot of unknown. How do you take care of? Can we add more data? Just to give you an example, just to add those 8 bulk sample, it needs 8 months to do the whole procedure. So data is expensive. So we thought, is there any way we can include the physics or feature in our Gaussian process regression? So the very first thing we did, we take the math minor features and try to include that into a Gaussian process regression and see whether our model prediction will improve or not. So here you can see, this is the very left side. I have a map minor prediction. I get the second generation model and combine together to get the feature-informed Gaussian process regression. But if I look at the uncertainty, map minor uncertainty, although it improved, however, it does not improve drastically that we are expecting. So we turned to physics and Gaussian process regression and thought, thus the physics-informed Gaussian process regression is better than the rest of those. But before going the advantages of the physics-informed GPR, just to give you idea what are the pros and cons of the data-driven machine learning, physics model, and the physics-informed GPR. So if I have the data, only data, then easy to combine an experimental insight into the data-driven ML. It's locally accurate. It can capture the complexity of the phenomena. However, we know that the data is expensive, sparse, and noisy. It has lack of interpretability. It is black box. We don't know what exactly and how exactly it's affecting. Although it's a feature informed, you can check the features, but there is a lot of lack of interpretability as well. It's locally deflected to the extrapolate outside the measured region. If you look at the physics model, the predictive window is based on the understanding. So it is really good if you have the model, but a lot of the cases, we often do not have the theories. It's often computationally expensive, and you cannot tackle the higher dimensional data sets, as I showed you in my previous example. And it's not easy to add the new insight from the experimental results or even in the other theories. And it completely ignores the uncertainty of the predicted model. Therefore, we combine both of those and get the physics-informed GPR. So advantage of the physics-informed GPR is robust and flexible. It requires the less data. It is interpretable. It lowers the uncertainty. It helps to identify the experimental outlier or may point out where the new physics might be required. So based on that, in 2021, Karen Quicksort wrote in Nature Later that the big data need big theory and the big physics-based simulation model too. So here we take the Clemens model, add it to the data-driven model, and we got the physics-informed GPR. But what exactly the uncertainty looks like? So if you look at here, in the left side, I have the data-driven GPR uncertainty. In the right, I have a physics-informed GPR uncertainty. So just to bring in physics, no new data, we actually lowered the uncertainty in the factor of 2. Our average uncertainty goes significantly better. So now if I look my search space, my data looks much better. So if I have less physics, I might need more data. If I have more physics, I might need to have, I can actually work with the less data in my cases. In some of the cases, some physics and some data might play a critical role to get the robust model as well. So after getting all this model, we do the recommendations. So here you can see our best model is the physics-informed GPR. So we do the prediction and uncertainty. Based on that, we recommend what material to synthesize next. I'm not going to talk about the Bayesian optimization part because it's itself a talk itself, but we are at a stage where we are doing the synthesis, structural characterization, and property measurement. We did the exact similar stuff to discover the new material. So here I'm searching for metallic glasses. So metallic glass is really interesting material because it's almost twice even higher stronger than the stainless steel. It has an excellent wear resistance and corrosion resistance property. It has outstanding formability, and it has a larger elastic limit and low cost. In 2017, Dr. Liu published the results that only 1,000 metallic glass have been published so far, and there are a large region where it's not published the metallic glasses. So here we are trying to find the metallic glass as well as the desired property. So we started with the database with last 60 years, compile with the physiochemical theories, and get the glass formability model. For the mechanical property, we create our own data sets and get the model for the wear resistance. After getting both model, we do the sputtering, where you can see that each spot represents the different compositions. And we do the high throughput X-ray diffraction and get the nano indentation. After getting all these results, we put it into the model and iteratively improve the model. So this is the matrix we used for the glass formability hardness, and choose one of the material which is fascinating is iron niobium boron. So if you look at the glass formability map, in last 50 years, people are only looking at here, so they never find the glasses which is stronger than 24 GPa. So in our case, we got the hardness around 24 GPa, couple of them, and also the wear resistance material. So if I compare now this hardness and wear resistance with the other material, you will see the hardened steel is somewhere here, which is 7 GPa. For example, razor blade is the hardened stainless steel. A lot of the carbide and the nitride material have low wear resistance. However, this study shows this is where our new material finding. And some of them actually comparable to the diamond-like carbon with much lesser cost. And we also filed the patent for this particular material. Using similar technique, we also did some corrosion mapping, high throughput manner, and machine learning, and got some exciting results as well. But we really wanted to do the autonomous closed loop material discovery, because as the dimensionality of complex compositional space rises, the high throughput synthesis protocol become increasingly difficult to scale up and synthesize the entire targeted space and characterize it as well. So the goal has to be guide the search to a desired region of the targeted space. The search takes here the iterative aspects, started with the high throughput search in a lower dimension in a simplified targeted space, use that lower dimension result and estimated the next search direction by the Bayesian approach. So we started with the high throughput synthesis, do the high throughput characterization. Real-time data reduction is one of the key for autonomous closed loop alloy design. And finally, gave the prediction and uncertainty for active learning and close the loop by recommending the next material. So here, the example I'm going to show you, it's Gilad closed loop autonomous system for material exploration and exploitation. Tomorrow, Gilad going to talk about the part he worked on, but I'm going to talk about what we did at SLAC to find out the composition with largest difference in the optical band gap in phase change material. So if you look at here, we use the active learning physics to get the synthesizing the material. After getting that, we perform the high throughput X-ray diffraction. This happened at SSRL. You can see there are a lot of computers, SPEC, Dexela, Express 3, all these things are communicating each other. And we did the real-time data reduction. After getting the real-time data reductions, we analyzing the phase mapping on the fly. At the same time, we also get the information of the band gap. And using both information, physics first map, we got the Bayesian optimization to select which material to synthesize next. So if these things work, you can see this is where the Python on-the-fly data processing happening, and this is where my active learning code is. So as soon as it goes from one point to another point, it started to reduce the data here and give information to this code. After getting this, it informed to the spec to get where to get next experiments. So if you look at now the iteration number versus percentage of deviation, if we only do the random 177 run, for example, all the samples in this thin film, you will see that it will take the 90 hours to complete the search. However, if you do the Gaussian process regression with upper confidence bound, it's going to take 100 runs. We tried the physics informed GPR with upper confidence bound. It takes only 19 runs to complete the search. So we not only found something interesting which is better than GST 225, it's also find it's in between the boundary region where people are not looking for it for a long time. So the challenge ahead, if you look at in this scenario, is the latency between the recommendation and the faster high throughput synthesis capabilities, especially in higher dimensional space where making the sample is really hard. Also, the dynamic range of processing conditions for multiple principal alloy systems make the scenario even difficult. The real-time data reduction, another critical issue. Not all the experiment or the detector data capacity and reduction is not faster and not standardized everywhere. So this is another challenge for autonomous closed loop alloy design. So although we came across long time to do this kind of experiment for one example, but it's not standardized for every beamline every time. So we have to go long ahead before actually doing this kind of autonomous closed loop alloy design every single experiment. So in summary, I showed you the strategies to design the new materials. I also showed you the ML-driven material discovery. And finally, I gave an example for autonomous closed loop experimentations. And thank you for listening to the talk. This work wouldn't be possible for many people at different places, especially my advisor, Dr. Apurva Mehta, who is at Slack. And thank you again. Happy to take any questions.
Thank you, Sushi. It was a great talk, and thank you for staying in time. Are there questions from the audience before I start to ask? Yeah, Maria, go ahead.
Hi, that was really excellent talk. Amazing work, nice. So I was wondering about uncertainty. How do you incorporate the uncertainty in the physics model and the physics informed GPR? The uncertainty in like the phase mapping, you know, when you do synchrotron experiments, or the uncertainty in the band gap when you do that measurement. All of those uncertainty, are they incorporated? How do we know we are doing it right? I would love to hear your thoughts on that.
So for the physics-based model, in the Gaussian process regression, we did instead of doing the kernel implementation, we did the mean value. So we can actually, it's not difficult. Once your Clemens model is there, we actually create a function of mean function and included that. We also taken care of different kind of information, whatever is available physics-wise, like, for example, speed of the material and other variables we include as a hyperparameter. So maybe I have one slide for you, which showed everything. Yeah, so maybe
I don't know if John has a follow-up to that or is it a separate thing.
So basically, I try to design implementing mean function, right? So you can create this one, or you can actually implement with the kernel. We also did the hyperparameter tuning. So in this case, is largest thermal conductivity, and the average sound.
Yeah, you know, like I have a certain behavior, the function of temperature, for example, for thermal conductivity. If I assume, you know, certain regime, but then, you know, it could be a different behavior if actually I guess wrong about the regime, you know what I mean? Yeah, so I guess you're right, having that flexibility is good.
Yeah, I think when we did the Bayesian optimization, it taking care of the prediction as well as the uncertainty together, and that helps a bit
Well,
to
no,
choose the next
the
experiment.
Bayesian gives the model uncertainty, but what I meant, more than uncertainty for the statistical model, what I meant was the physics, the uncertainty in the physics.
Oh,
In that case.
we don't have the physics uncertainty, right? Because physics doesn't give the uncertainty. That's why we try to implement the physics and GPA together, and that provide me uncertainty.
Well, I mean, I don't have as much confidence in physics as you do. At least our understanding of physics. I mean, there are times where I had to choose between different models that, physical. Anyway, we should not belabor that point. Maybe
no,
John.
but I think actually it's a good point, because your point is much more like, of course, like it's always the status of where we stand right now, right? So we believe that this is true, but the question is like, how can we refine maybe also our physics model? Because maybe we have forgotten to include something, or maybe the mechanism is different than we thought, right?
Yes, and we do find that the physics does not always capture everything, right? So there might be new physics required, and that need actual experiment more elaborately to do find something interesting. And that's a struggle actually. And we do find something like this actually in our experiment as well. So if you look at this one, I don't know whether you can see, so the physics does not able to capture that. However, the experiment can capture that. There might be new physics required, but it's required a lot more study to say that the physics needs to be changed. This is a long claim, right? With only based on the experimental results. So
let's say the model has to be changed, not the physics.
Oh, it's not changed, but you have different regimes, right? All the we use are phenomenological models.
Yeah.
They only work in certain regimes.
Yeah.
Maybe we'll let John ask his question.
Yes.
Okay. So great talk, and I'm going to put you on a spot here with probably a fairly difficult question. So the kinds of things you're talking about, where like you have a phase space triangle, and you're trying to optimize something in the space, is by its very nature interpolative, right? So you're trying to find some linear combination of these endpoints that gives you what you want. So what's the opportunity space, or what would we need to do to be extrapolative using AI and these physics-based models, and think about how you get outside of defined phase triangles, or explore new spaces?
Yeah, I think that's why we started with the global model, because this Gaussian process regression mostly at the local region, like I already know the space and trying to optimize in a local region. And if it is like completely unexplored region, we have to start with something like MATMiner, which is the feature-based, and try to understand the features in more elaborately to find out whether it makes sense or not. But usually, at least for GPR, what we saw so far, even with autonomous experiment, we do find it's always you have to have very local region and optimizing the stuff. And I mean, it's a 5-dimensional space, it's quite larger, but even though it's kind of local, not completely global model. If that makes sense to you, or if I gave the answer.
Okay, if there are no other questions, I would like to thank Sushi again for this very nice talk. I would have more questions, but I think we would have to move on now. Yeah, thanks for the virtual applause here. It's always a little bit awkward with what we are doing here. So our next speaker here is Yan Zheng, also called, you go by Helen, is this correct? I'm sorry, is that I have to ask?
Yeah, I was in Canada, yeah.
Yeah, okay. So Helen is from Berkeley Lab, and they've done some very nice autonomous experiments recently. So I'm very curious to hear what you have to report about the latest news here.
Thanks. Thank you for the introduction, and thank you for the invitation. Let me share my slides. All right, can you see my slides?
Yes.
All right. Hello, everyone. Good afternoon. Thank you for the introduction again. My name is Yan. I'm a staff scientist at Lawrence Berkeley National Lab, And today, I would like to share with you our very recently up-running A-Lab. It's an autonomous laboratory for inorganic solid-state synthesis. I will be sharing some photos, videos, and as well as our machine learning for XRD stuff that might be more relevant to this workshop. So we want to do what in experiment, what the materials genome has been doing to by using high throughput computational materials design to innovate new materials. So we want to move on to the next challenge, that is to accelerate materials synthesis by 100-fold or maybe even more. To do that, we are implementing this so-called closed loop workflow that can autonomously iterate towards a successful synthesis or experimentation of a certain target. So here I want to introduce the A-Lab, and that has been, we started this whole build since early 2020, the very beginning of pandemic. In February, mid-February and February-ish, we started to have everything connected and started to generate results. So this A-Lab is still under expansion to other capabilities, but so far at this point, we are focusing on inorganic solid-state powder material synthesis and its associated characterization. So to do solid-state synthesis, we start with a powder dosing and mixing unit in this box, which I will show pictures later. And we have also implemented a bunch of furnaces that can do atmosphere controlled heat treatment of the powder materials. And there are several robot arms running in the lab to handle sample and the tools. And they are also trained to be adaptively interact with the environment that might be always changing due to different research results. And of course, we have an analytical instrument. At this point, we have a tabletop X-ray diffractometer and SEM together with EDS. And for the computer part, we have written our own API to control all the workflow and the software of the instruments, as well as data management. So in this A-Lab, we integrate majorly computation, text mining, robotics together with machine learning so that this lab can do autonomously iteration towards a successful target, which now we are focusing on the synthesis problem. And since we are focusing on the solid-state synthesis, we also need a robot that can handle powder precursors all the way to powder products that sometimes bring new challenges as compared to the liquid handling setups. Along the line, like building this lab, the physical lab, since it has taken many years, we have been also developing AI machine learning models that can do data analysis as well as decision-making. Just want to give a quick overview of the workflow. We start with designing the target, which can be originated from many different resources, such as high throughput computation. And then we use our machine learning model that is trained on a text mine data set to recommend a recipe that might be the best to synthesize a certain target. Then the robotics platform takes the advice from this recipe recommendation to execute a synthesis in the platform and perform characterization of the product that has been synthesized. Then another machine learning model analyzes the data on the fly. After that, it feeds up the data, the results, to a decision-making agent to decide if further experiment need to be done. And if that is the case, what experiment might be the best that can reach the target as soon as possible. So to start with, as I mentioned, there are many ways that we can design a target. We may have a certain application that requires certain chemical space, etc. But for our very first project, we are doing this in a very explorative way. We want to see how many new compounds that can be synthesized using the setup that is available in the A-Lab. So our database for this target design is the materials project, which currently contains about 146,000 inorganic materials based on ab initio modeling on the known and the novel materials. So we take the data from this database and perform the screening. So just for some information here, the materials project right now has about 300,000 registered users, and people have been using this for all kinds of machine learning works and data-driven work, so using this database. So once a target is defined, the next step is to design a synthesis recipe that might be able to make this target. For our case, we have been taking advantage of a large text mining database that contains about 70,000 inorganic synthesis recipes that my colleagues have been extracted from using AI models extracted from 4 million papers following these text mining pipelines. So now it has synthesis recipes for a variety of synthetic methods, such as solid state reaction, hydrothermal soil gel, co-precipitation, etc. So use the information, the recipes extracted from these papers, we can then build a machine learning models that can recommend the precursors and synthesis conditions all the way to plan the synthesis recipes for the robotic platform to take. I'm not going to go through details for this because it has been published by my colleagues. So if you're interested, you can go through those papers afterwards. So once the target and the recipe is defined, then the A lab performs the synthesis in this setup that is right now located in one of the buildings at Berkeley Lab. So the current capabilities is, again, like focusing on solid state powder synthesis. And what this platform can do is that once we input a target, like tell the computer a certain target, it can go all the way to give us the face identification result from XRD, and all the way, everything is through API without any human intervention. We also build this platform so that it can handle flexible sample quantities ranging from about 0.1 gram all the way to 10 grams, since we wanted to do either like property testing as well as device fabrication afterwards, especially for those samples that might have promising properties. We also make it extendable so that we can add other synthetic method or add another analytical instrument to this facility. So the current facility contains majorly 3 stations that are integrated together. It starts from powder dosing and mixing unit and a high temperature heating unit, as well as a sample preparation unit for XRD and SEM. So here I have some videos to show. So it starts from this precursor powder dosing. This first robot takes the consumables from the loading zone, and then the automatic balance will start dispensing different kind of prescribed powders with their certain amount. So now it handles another powders and then perform a mixing of the powders with a little bit solvent. After that, dry out the solvent in a crucible that can then go to one of the furnaces. So the second robot arms waiting outside takes the crucible and then travel all the way to the pre-assigned position for this certain crucible, and then handle it all the way to one of the furnaces. It can either be these box furnaces that perform synthesis in the air. So each furnace can hold up to 8 crucibles. Or it can go to the furnace on the floor that on the right corner that can perform synthesis under controlled atmosphere. This is especially important if we want to synthesize some, for example, cathode or anode materials. So after the heating step, the last step is to retrieve the powder or the solid from the crucible and prepare it for the XRD and SEM. And the tricky part is here that after high temperature synthesis, it may form all different kind of forms of solid that might be difficult to retrieve. So once we have the fine powders, this shows how the robot arm dispenses the powders to XRD sample holder. And an important feature of this setup is that we want to make it as flexible and as robust as possible. So we have implemented all different kind of self-correction modes. For example, when the robot arm dispenses these powders to XRD sample holder, one very important parameter is that it needs to have a good coverage as well as a flat surface. So we have implemented a vision system that take pictures and then analyze the coverage of the powders on the sample holder. So the robot arm will keep trying to dispense until it reaches a certain threshold. And in this video, at the left corner, we also have a balance that measures each time how much powder has been dispensed on the sample holder. So that if it's tiny amount, then it will just keep dispensing in another run. So here shows another video that this powder is relatively easy to handle because it flows very well. But in other cases, it may not look like as smooth as this one. And after that, it will flatten the surface before it is sent to the X-ray diffractometer. So this is one type of kind of uncertainty or variation among different kind of powder products. And the other errors or uncertainty that may happen in very commonly in this kind of robotic lab is position offset. So what we do in this case is that the robot arm will handle this tool and touch the side of the crucible rack each time to make sure the rack is there at the right exact location. And if it's not, then the robot arm will correct or recalibrate its locations right away with reference to the position of the rack. So only after then, it will insert this tool underneath this crucible rack to make sure that nothing is mispicking. Okay, so here's just some kind of examples of this setup. Once this is done, now what we have is raw data from XRD patterns, and usually we use commercialized software to analyze this. But since we are aiming for high throughput and we're also aiming at fully autonomous workflow, it's important to have models that can help us analyze the data, in this case, XRD, on the fly with a high confidence. So I'm going to go through just sort of briefly like how our machine learning model works for this case. And specifically, since we are using just a tabletop lab X-ray diffractometer, it does not have great quality as what we can achieve at Synchrotron. So we want to build a model that can handle the trade-off between speed and accuracy. In this case, if we run it very fast, like on the left side, this is usually the case when we run a scan for like 10 minutes or so. While on the right side, it has a much cleaner pattern that we want, but it usually takes half an hour that can sort of reduce our throughput. So what our solution is to sort of spend more time on the 2 theta range that will give the most information. So to do that, we are building adaptive XRD algorithms, which contains majorly 3 components. The first component is that we need a model that can do the face identification from raw XRD data, telling us what phases might be present. And also we need to handle not only single phase, but also multiple phase XRD data. And the second component is that we need a method to analyze the uncertainty or to quantify the uncertainty to tell us the confidence of the analysis to decide if the X-ray XRD need to scan more in a certain location. And the third part is to decide where the diffractometer should go back to scan or spend more time on. So for the first component, we are using a convolutional neural network which we have simulated patterns and from experimental and model structures, which we majorly took from ICSD and the Materials project. For the simulated patterns, we also consider the experimental artifacts such as peak broadening, intensity variations, and also offset into theta that are often seen in real experiment. So after that is done, we will have a CNN model that can handle multiple phase XRD data. So with that model, the second part is to estimate the confidence. And our approach is to use this ensemble method. So basically we have 100 CNN models that they are different in a way that they are sort of connected differently. And then each model will give a prediction, like model M may say, oh, these peaks belong to phase 3, etc. And then the confidence is calculated by sort of the percentage of the models that predict that certain phase. For example, here, phase 2 has a confidence of 65% because there are 65 models out of 100 predicted phase 2 as the phase that is in the XRD pattern. We also find correlations as expected that the higher the accuracy, the higher the confidence of the prediction. So, so far we use a threshold of 50% of the confidence. So if the confidence is lower than 50%, then the model will say, hey, we need to do a rescan of a certain area. So to decide where the rescanning should happen, we use the typically used class activation map CAM to sort of find out the regions where this will matter the most to the model's prediction. So in this case, we find out that, again, as well expected, the highest peak usually have the highest CAM value that are sort of gives the most important decisions to the model. So with these 3 components completed, we can then apply it to a real case. So to give an example, when we start with an unknown sample scanning, firstly, the diffractometer will perform a very fast initial scan, 2 minutes. So 2 minutes is considered as short, pretty quick for a lab-based XRD. And this is usually enough to make a preliminary prediction if the crystallinity is not that bad. And after that, the model will pass the initial pattern to a pre-trained CNN model. And this pre-training is usually done in a well-defined chemical space. And we usually perform this before we put a target into the A lab. And then the prediction is usually done in a few seconds. And then we also calculate the confidence. And the confidence is low, then we calculate the CAM, and then it will tell us which area the rescan should happen. So after the rescanning, then the updated pattern will be fed back to the CNN model again to make an updated prediction. So something like that. And we usually find that the areas with the largest differences in CAM between 2 different phases, prediction in different phases will usually gives more important information that distinguish these 2 phases. So now the model tells the diffractometer where it should go back or where it should extend, then the diffractometer will rescan that area. All right, so you may realize that I only go through like very briefly how this works. This work is majorly done by a graduate student, Nathan Saminsky, and he has the code ready at his GitHub as well. So to summarize a little bit of this XRD pattern, machine learning XRD result, we have this model that can send feedback to the XRD, and so that we can adaptively control the X-ray diffractometer as well as perform on-the-fly data interface identification. Here I have just a very quick video that shows how it works in real life. So it starts with a very fast initial scan, like 1 to 2 minutes. Then the AI or the model suspects the impurity peaks and perform a focused area scan. And then these 2 patterns are integrated together. That will enable a more accurate phase identification. And we found this particularly, I'm not showing slides here, but we found this particularly useful for in situ XRD with lab XRD, like the blue one, for example, since the quality is usually pretty low. And we found that once we implement this, we can have a better analysis on the short-lived intermediates for particular. So we hope that more researchers can find this useful in their research as well. All right. So now we are also implementing, developing some machine learning algorithms for SEM and EDS. Now we have a model that can perform automated, like autofocusing to take a picture. Just got stuck there. It can also perform automated segmentation of particles so that we can do particle analysis of this kind of samples. And now we are sort of merging the results from EDS elemental analysis with XRD analysis so that we can have a higher confidence face identification of different phases that might present in our sample. So with this analysis data, then what the whole workflow need to do is to decide to find out if we have synthesized a target, and if not, what we should do the next. So this is usually the case, like when the initial prediction of the recipe doesn't really work as we expected. So we have implemented algorithms that can learn not only from the successful ones, but also from the failed synthesis outcomes from the previous synthesis that can be used as knowledge for the decision on the next set. So for example, if we run precursor set 1, we choose these 3 precursors, we heat them up to temperature T1, and we find out 2 intermediate phase formed from as a result of the combination of this precursor set. And when we further increase the temperature, we find out, oh, these 2 intermediates may not really react with each other. So we consider them as inert byproducts. And then in precursor set 2, where we choose 3 different precursors, and when we react them to a certain temperature, we also see the inert byproducts that we have seen, the model has seen in the previous set. Then the A lab will not continue this path because it will predict that they will not react together. So this set will be abandoned. Instead, it will go to precursor set 3 to choose another 3 different precursors that might give more confidence in achieving the target. So this is just show like a brief idea of these algorithms that we have been continuously developing. And these are based on mostly on the reaction energies between different precursors that we want to preserve the reaction energy or the driving force as much as possible to form the target rather than the intermediate phase. So see my time. Just to end this presentation, I want to thank you, my team and my supervisor, Gerber and Cedar, and as well as all the funding sources that have been tremendously important and supportive for building up this lab. Thanks.
Thank you very much, Jan. This was a very, very interesting talk to me. I guess also for many other people. Does anybody want to start first this question? Yes, Maria. Go ahead.
It's a very nice talk, Jan. Have you guys sort of try to see if there were errors in the literature? Like,
yeah, for sure.
I'm all about errors and uncertainties today.
Yeah. So, well, I'm not an expert, so I may not state everything sort of correctly, but as well, as far as I'm aware of, my colleagues have spent a tremendous amount of finding out errors, especially like missing pieces in the recipes. As you can imagine, like the community is not really following like a strict standards of how to report synthesis, right? So, so what we did before, which I also participated, is that we will sort of randomly select a certain sort of recipes or literatures to and compare what human will interpret versus the text mining model. And it usually the case, like the error usually happens when there are missing pieces there, or like people use different terminologies to describe the same thing. Like for example, heating. It can be heating, can be annealing, calcination, high temperature treatment. So all those kind of different words. And we are still sort of expanding our capabilities in considering all the different kind of terminologies and the way people write their sentences.
Yeah, absolutely. I think John has a question.
Yeah, so this is very impressive. I have a question. So when you, so just thinking about how humans do this kind of thing. I mean, I've done this. So if I make a mixture of things and I heat it up and I pull it out and I do an X-ray diffraction pattern and I can identify 3 phases, it could be for a couple of reasons, right? I mean, that could just be the thermodynamic phase assemblage for the conditions I used, or it just could be that I've got some kinetic trap. And so what I'll do is I'll go stick it back in the furnace and heat it up again, or change the conditions in some way on that exact same sample so that I know how it's changing versus thermodynamic variables. So do you do similar things, or how do you decide that what you are looking at is really representative of the chemistry of the system?
Yeah, well, great question. This is exactly what we are doing right now. We're improving our models. Well, like what we usually do, what the model usually do is that it will perform, for example, a few hours synthesis at a certain temperature. Let's say 900 degrees C for 4 hours. And then if it doesn't see the target at all, or if it sees kind of, let's say 20% low yield target, then it will automatically sort of go to higher temperature or like longer heating time to see if the yield has been increased or not. If it's increasing, then it's almost indicating that it's kind of like a kinetic thing, because we need like a more time for the ion to diffuse or something like that. And if it's not, then the model is kind of, it's hard for the model to decide what to do, because it might be like a very super sluggish kinetics that is still trapped in the kinetic state, or it can be a thermodynamic issue that our thermodynamic model didn't predict very well. So this is exactly the thing like we are still figuring out. But on the other hand, solid state synthesis is relatively kind of representative for thermodynamic synthesis, like equilibrium state, especially compared to other types of like low temperature synthesis method.
Well, I don't disagree with that, but I could pull up my logbooks in my lab and show you a lot of examples where that's not true. So I think that this is a terrific platform, and actually it should be great to be able to kind of explore these kinds of problems in a systematic kind of way. So I'm super impressed.
Thanks.
Suchi was the next one having a question.
Great talk. I was wondering, your model, especially the XRD model, can be implemented for other universities, because universities have XRD stuff. And a lot of people come to the beamline with very, very bad sample, and they say that they are not able to get the data. A lot of screening time they wasted. So is it actually they can take your model and implement into the lab XRD in their university?
We actually have many kind of users reached out after reading the papers, because the codes are there at the GitHub. It's free access. And we are also trying to make it like easier to sort of implement it. And it's actually pretty straightforward. And we have, since we are next to ALS beamline, we have been also sharing this with other ALS users so that they can use them to just at least to give kind of a rough estimation or interpretation of their in situ results, because it's usually hundreds of patterns, right? So this kind of machine learning models is really like convenient to give at least a first sort of understanding of what has been formed there.
Thank you.
Simon.
Thanks very much. Yeah, I wanted to ask a question about the robotics part of it. So I don't really have a feeling for how difficult or hard it is to roboticize everything, how much like overhead in time it takes to get it all set up and working, and also the cost, like whether it's expensive or cheap compared to other kind of experimental equipment. Like how is this only going to ever appear as a kind of shared facility at a national lab, or is it just everyone will have a robot in their lab sometime soon? What's your view about it?
Well,
your
I
experience?
feel sometime soon, even now, many people have a robotic arm in their lab, or especially Beamline has a lot of sort of robotic arm sort of around helping out with certain tasks. How difficult or how time and capital consuming it is really depending on the scope of research, like what kind of tasks we need a robot to do. Like in our case, we have to sort of start from scratch for most of our setup. So it takes much more effort, to be honest. We started like March 2020, sort of in designing what is doable and what is important and what is doable to be done by robots. And it's only like until February this year, we have everything ready. So it indeed takes time, but I can see
how many people like
how many people
are working on
so the
that?
core members, I would say most like is core members are about 4 to 5 people, like including myself. I was a postdoc, and then there are 3 graduate students, and later on we have more people sort of helping out with some other tasks, but in general it's like 4 to 5 people. And another important thing is that all of us, we didn't have background in robotic sort of platform. So we learned while doing this, building this up.
Yeah, there's a robotic arm at the XPD beamline at NSLS2, and as far as I know, it's never been made operational. So just there being robots, and you could buy a robot for something like $40,000 or something, right? And it's not even it's the same as a high temperature furnace or something. So but it seems like actually getting it to produce value is what costs much more.
Right.
I would like to add here also my question, because it's a good point. So actually, I believe it's much more like you have to go through the first bump of energy, right? I mean, as soon you have learned it, how to use a robotic system, then becomes easy. I think just the learning curve how to do it is a problem. So my urgent question was, I just want to ask is like, I love your autonomous lab, right? And my biggest dream would be to have something like this at a beamline. And because at least part of it would be very interesting to profit from the better quality of X-ray data, but also to combine it. That's my personal interest is with in situ synthesis, right? So because if you really can do it in situ to follow all the processes with high quality data with decent frame rate, I think you learn even more and you can feedback even faster, right? What do you think? I mean, what is your footprint? What is actually the physical size of your lab? What's the how many square feet did you use?
Oh, it's 600 square feet.
600 square feet. And do you think my idea is reasonable, that this is something that's doable, or is the maintenance of such a lab so high that you would sacrifice too much beam time by working on the maintenance?
I actually see like robotic handling, like sample handling or instrument handling, it's more suitable for beamline, because beamline, my understanding is well designed and it requires precision and like a very high robustness. That is what like robot arms really good at.
Yes.
And also another thing is that I feel like most part beamline needs a robot is to load and unload samples. Maybe sample preparation as well. Sample preparation and load, unload.
Yes.
So, yes. So I think implementing robotic sample preparation and handling are very doable and can be done like kind of in a short term of time.
Yeah. John, maybe you want to second me here.
Oh, no, very, very quick question. So handling is important. So you didn't show a video. Does the robot actually load the samples that have been prepared on an X-ray slide or holder onto the Eris
Yes.
diffractometer?
Yes.
Okay.
It's
So there's no human needed in that point. So it's all automated through that.
It's all automated. Like when I say without human intervention, it's literally. So what we do, like started the whole setup is we still need to put the consumables into the loading zone.
Yeah.
Consumables and chemicals like precursors.
Right.
And
So
after that.
one last question about that, Uta. So lots of times if you buy a chemical from some stock house, it's not what you think it is.
Yes.
So is there, or sometimes they need to be pre-prepared before you actually can do something with them, like weigh them out. So how do you handle that kind of problem?
What do you mean by weigh them out?
So you want to make some compound, like for instance, it has lanthanum in it, and you use lanthanum oxide as a precursor.
Yeah.
Because that's a nice one to use, but it's going to be contaminated with carbonates and hydroxides and water and crap. So how do you deal with that problem?
Oh, so well, manually, I've been dealing with that problem. I heat it up at like 700 degrees C for a few hours to decompose, which can be sort of easily implemented in this lab, which would require kind of a pre-step, sort of to do a pre-XRD, for example, XRD, SEM, EDS together on all the precursors that we receive from the vendor, which is kind of like should be a more standardized practice for experimentalists, although we haven't really like.
Yeah, I would definitely suggest implementing that. We always do this because lots of times you open a bottle and it's not what it says it is, and then you wait a lot of time. Well, the robot waits a lot of time.
That's true. That's true. Yeah, it may get to an impurity that is not the reason of a certain precursors that we think it is. So, great point.
Yeah,
Maria, is this a short one?
No, I want to say we should move on to the next topic because we actually
yes. That's what I. Yeah, that's what I also wanted to say. We need to move on. Thank you very much, Jan. This was really a great talk and very enjoyable. Our last speaker for today is finally Taro Hitosugi, and he is from the Tokyo University. I mentioned before, thanks again. It's wonderful that you are willing to give this presentation here at this horrible time for you in Japan.
No, it's okay.
And yeah, I think you have to switch into presentation mode. So I think your talk will be on thin films of titanium oxide, right?
Right, and also other materials as well. Good.
Okay, very cool. Thank you very much.
Yeah, thank you, Uta. And then hello everyone. It's 6 o'clock in the morning in Japan, and then it's my great pleasure to give a talk in this conference. And today I'm going to talk about this thin film synthesis. And I'm very happy to show that we fabricate thin films autonomously, and also we characterize for many aspects autonomously, automatically. And this slide shows our vision of our research. So far we have been doing experiments manually. It's like rowing a boat to this island. And now AI and robots has come into our lab, and it's like getting on a motorboat to this new materials. But I think this stage is only just speeding up the research. It's just increasing the efficiency. So what we want to do is to go to materials something we are not expected. I think that is a goal. And nowadays we can utilize reliable data from autonomous experiments or automatic experiments and collect many data. And then we have a bird's eye view. And from that, finding a new islands different from here. We may find a good place to find materials here or good islands around here. So we should utilize data to find something very, very different from the conventional material. That's a shift in the paradigm shift in the quality of materials research. That is our vision. So for doing that, I want to talk about two topics today. First one is the optimization. And the other is the finding new materials, something unexpected. So for the optimization, search area is given by human researchers. So we set the parameters to tune. And then this part, I think this is a proof of concept is complete. Not only our group, many researchers report this optimization. And the challenge is spreading this technology. There was a question about spreading this robots in sharing facility or even in the usual lab in university. So I think that this spreading this autonomous research is very important. And the robot cost is getting low. And then the software for controlling robot is now really available and become the teaching of robots has become very easy now. So I wish many researchers use the robots in labs and then automate their research. And I'll talk about the titanium dioxide optimization. And also the second one is very important. We have to go something like a extrapolated or something we want to find is serendipity. So I'll talk about finding electrode material when searching electrolytes. And also talk about our new system. So this is how our research goes. So we want to maximize the functionality and we use Bayes optimization. We use like a Python code and then UCB or EI. And then we tune the hyperparameters to reduce the number of trials. So this is very important when we think about the process window of material synthesis. We have to tune the good hyperparameters to reduce the number of trials. So this we input the knowledge of making materials by our hand to this Bayesian optimization. And this Bayesian optimization indicate the next synthesis parameters, and we grow thin films using sputtering, and then the robot transfer the sample to measurement system, and then report the data. And then this predict again. This we call closed loop. And this is our lab. So you can see that I am here, and then you can see the size of our equipment. So we have a robot. This is a transfer robot, and in the center, and then these are chambers. There are 6 chambers around. So there's 6 chambers on the sputtering machine and then measurement machine. So first I'll show in the one-dimensional case. This just a animation. This temperature, and then this curve is that if we do all the experiments, we can find this white line. And then Bayesian optimization predicts and fabricates thin films. And then the sample is transferred by this robot to this measurement system, and then measure the ionic conductivity or electrical conductivity. And then data goes back and then predicts again. So this goes on and on without human intervention. Now computer predicts 175-degree. And then the film is deposited, and then the sample is measured again. So this goes without human intervention, so we can find new materials quickly. And then we now want to share this with many people, and then so that the many people can log in, our student log in from their home, and then start experiments or monitor the experiments. So I wish the system is implemented in like a synchrotron facility, and then I wish it's combined with a synchrotron measurement system. And this is how it works. So this is a actual experimental data for the two-dimensional optimization. This is annealing temperature, and then this is oxygen partial pressure, and then the two-dimensional optimization. So we want to maximize the electrical conductivity of titanium dioxide. And this is how it works. So these black points are the computer predicts, and the research is done autonomously. So it's like making a phase diagram quickly. And then soon this red part is the highest conductivity part. And so the computer finds out that this oxygen partial pressure and annealing temperature has the highest conductivity. And then one important thing is that we can collect these process data. It's not the best one, but we call this negative data, and then all stored in a database. So we can utilize these data for the next deposition or finding next materials. So we proved that we can increase tenfold in the speed of optimizing the samples. And we want to use this technique to find something new and something unexpected. So we would try to find new ionic conductors. And then we set two types of targets to the sputtering: lithium phosphate, and then this lithium aluminum germanium phosphate. We call this LAGP, and co-sputter on a substrate. And then we measured AC conductivity measurement, and then from that data we obtained ionic conductivity or electrical conductivity, and then the Bayesian optimization. So we did this in a closed loop manner. And this is how it goes. So we tuned annealing temperature and output power of this LAGP target. So this is a composition. And we can see that it's like making a phase diagram. And then we see this red part is a high conductivity. We see there's two regions that has a high electrical conductivity. And then we measure this, measure AC conductivity measurement. This is we call this call plot. This is a frequency dependent, real part and imaginary part. And from this, usually we measure this ionic conductivity using this call plot, or we call Nyquist plot. And if we see this region 2, we have this type of curve, and this is a very represents this ionic conductivity. So, and this is a Arrhenius plot, and we find that the high conductivity of 3.4 times 10 to the minus 6 Zms per centimeter. This is a higher than original target materials. The original target has lower ionic conductivity. So we can say that we find a new ionic conductor using this autonomous system. But I want to emphasize that we find something unexpected. That is a fun point for using this system. For this region 1, we see AC impedance different from this normal lithium-ion conductor. So we thought that this region, we see both ionic conductivity and electronic conductivity, so that this can be used as electrode material for a solid-state battery. Actually, we fabricated a solid-state battery using this electrode. We deposit lithium phosphate and then deposit lithium, and then the complete solid-state battery. And we measured this property of battery, and then we found that this is a new amorphous electrode materials. So we aimed for electrolytes, but we measure many properties at once, so we can find that it is electrode materials. So that I think that the very fun point for utilizing these autonomous system. And also for the algorithm, we utilize this phase diagram, finding a phase diagram mechanism, algorithm provided from Tsuda from the University of Tokyo. And this works very efficiently to find out the phase diagram, fabricate a phase diagram. And I said, I want to find something unexpected. So we combined many characterization apparatus in this system. So this is what the basic way of research for the material science. If you are like a battery researcher, we only measure ionic conductivity and then don't measure other properties. They may have a very nice properties, but we don't have time or money to measure these properties. That's why the data is not complete. So, but if it's a robot, it can measure all the properties and find something unexpected. And also we want to combine the process parameters. This is very important for inorganic materials. The properties is very sensitive to process or synthesis parameters. So we want to have a complete data set and find for something unexpected. So for that purpose, we fabricated a system like this. So once we fabricated thin films, and then we transfer samples to many equipment, and then get all the data and find something unexpected. And for this, we collaborated with many companies like Shimazu, Rigaku, or Jeol and Horibab. And we also collaborate with the other Hitachi High-Tech, those companies. And then we want to make this like a plug and play. If you buy some equipment from these companies, and then you just connect those systems, and then I wish it could be an autonomous or automatic system. So standardization, this is important. And these companies are different, like Shimazu, or this Rigaku is X-ray diffraction. This is a SEM, this is a Raman, and this is a transparency, optical transmittance measurement. So these are different companies, but I asked them to use same sample holder so that we can transfer one type of sample holder to all those systems. And also we standardize the how we can connect these each other. And then we also protocols for combining or this system, and then we share those protocols. And actually, this is a system we set up in Tokyo. And then here's a load lock, and then there's a sputtering machines, and then there's a robot transferring a sample. And this SCM EDX is directly connected to this vacuum system, and then transfer the sample to SCM. Also, Raman directly connected. And we take out this the sample to the air using this vacuum chamber, and we use this robot system to transfer the sample to this Rigaku X-ray diffraction. And this is how we transfer the sample to X-ray diffraction. So this is a Rigaku's X-ray diffractometer. And then we use these robots to transfer samples. So now this window opens. Wait. Yeah. So this window opens, and then the robot, we use 1 centimeter and 1 centimeter sample, I think, and then thickness of 0.5 millimeter. And this robot catches these samples from the thin films deposition machine, and then transfer into this Rigaku X-ray diffractometer. After transferring this sample, the X-ray measurement is done automatically. So this is how we combine all the measurement system. So we directly connected sample, transfer sample to the system, or we take out to air and then transfer 1 centimeter by 1 centimeter sample to many other equipments like this X-ray diffractometer or this transmission photospectrometer. And also we have to standardize the data format. So nowadays, if this is a Rigaku or JO system, the data format is different. And then we find difficulty in storing the data to the database. So all those companies we collaborated, we asked them to use this this format. This will become a Japan standard from this year, and then many company will output this data from using this format. So all the data format is unified. So we don't have to make a converter for storing data or analyzing data. So all the data is outputted from this this format, and then directly transfer to the cloud. We use AWS, Amazon AWS, and then analyze data on this platform. Also, we want to include this process data. This is a bit problem because there is no standard to digitalize this process data. This the sequence of data, and then how we store the process data. I think there's no standard way to put into database. So this is what we are working on. We want to standardize how we how we describe the process flow or incorporate actual data. So that's what we are working on. So I want to summarize my talk, and then we are working on the development of autonomous research, and then we have to think about how we can spread this technology. So we only talked about the thin films growth, and this is very good for autonomous research, but we should focus on more like bulk materials, like the previous talk. So we also work on those inorganic bulk materials. And also, I think this standardization is the key. And then we have to work internationally to go for this like a plug and play, and then many labs can introduce those autonomous system. And also we want to share this system, and then we are planning to share our system worldwide, so that from the United States, you can log into our system and fabricate samples, and then we can return the data to you. So it's laboratory is like a service. And then we should go to something unexpected. So I think that the multifaceted measurements is very important, and to find something unexpected. So I would like to stop here, and then thank you for your attention.
Thank you very much. This was a very interesting talk, and I'm really admiring the data standardization. Because
yeah, that's very important.
It has to be a gigantic effort to really get everybody signed on this. Before I continue with questions, I would like to give the floor to other people who would like to ask something. Other questions from the audience? Simon?
Yeah.
Please go ahead.
Hi.
Yeah, hi, that was wonderful. Yeah, I'm also excited about data standardization. So I just went and Googled MAI-ML, and there's nothing in the US Google about it. Is the standard published? Like, how do we learn about the standard?
Yes, this is going to be standard from later in 2023. So this standard, this information is still not open yet. So but only limited people is now working on this for the standardization. So soon we can open all the standards. So please wait for a little bit more. And then many companies can adopt this system, so that you don't have to fabricate a converter anymore.
I'm looking forward.
Yeah, is it working? Is it working for some United States, working for the standardization of this data from many companies?
There is an effort. There's a thing called MARDA, which is materials something, but it's
Materials Research Data Alliance.
Yeah,
I am the acronym whisperer today.
Yeah. So we take a different approach in the US, where we make everything open and everyone fights about it until it's kind of finally converged, and then that's the standard. I guess it's much more autocratic to keep it secret and then publish it without getting input from people. I don't think this would work so well over here, but it's obviously actually a good approach for getting the job done.
I see.
Yeah.
Maria, you would like to add something? A question?
Yeah, I was curious about the setup. Compare. I really like your octopus, right? The fact that you can do many different measurements. And I one of the best part I think about your setup is that, you know, you do the measurements even if you didn't know if that material was good for that, like just have
Yeah.
sort of, you know, the unexpected built in. One question I have about that setup though is that it doesn't seem like if I wanted to add another synthesis chamber or another experimental characterization technique, like, you know, I want to measure one more thing, it doesn't seem like that allows the scalability, you know, versus the previous talk, the one that Yan showed, they using the linear track, maybe, you know, that, yeah, like what were the, maybe I didn't get that correct.
Very good question. So our system is, it's like a module, and then you can just like a plug and play, and then there's a ports available, and then if you want to measure something, you just connect it. So the sample holder is if you can use the same sample holder used in here, then you can transfer the sample to the system you want to add. And also we can expand, as you can see this, we can connect
so you can just add more circles.
Yeah, this circle we can connect, and then we can expand so that you can measure many properties.
I see. Okay. So yeah, I was like looking at that circle and thinking, you know, once it's filled, but actually you can add another circle next to it.
Yeah, next to it. And then if the room is large, we can expand.
Your instruments are also on wheels, right? Does it mean you could also wheel it out and wheel something else in?
Sorry.
I've seen your instruments are also on wheels. So in principle, you could also wheel them out and wheel something else into the line, isn't it? That you could replace them completely.
So your question is that some you want to replace this Raman to other system?
Yeah, also the big chamber. You could take out the chamber and replace it by a different chamber, isn't it?
Yeah, of course. If you want to put the MBE, then there's a open port, so you can put MBE here and then transfer sample autonomously. Automatically.
Okay, thank you, John. You're next.
Yeah, thanks. This is terrific. So I wanted to ask a question about kind of pinch points in this process or rate limiting steps. So I imagine, you know, you can do an X-ray diffraction pattern in a few minutes, but if you need to do some kind of cryogenic magnetic measurement, it might take a few hours.
Right.
The synthesis itself might take hours or days. I have no idea. So where are your pinch points in the process of optimizing materials or discovering new things?
That's very good point. Very good point. This for the thin film synthesis, we need like 1 or 2 hours for one film. So that's the most time consuming part. And if you said that if there's a physical property measurement that takes time, then that limits the whole throughput. So we have to set that 2, 3, 4 same apparatus to do it in parallel.
Right.
Yeah, that's one problem. Yeah.
Right. That gets costly, right? I mean,
yeah, that's the one bad point. Yeah, I agree. But we can program, and then if there is one apparatus that takes time, and then other samples are waiting, so other sample can measure other properties first, and then go back to this time-consuming part.
Yeah, I'm sure that there's some sophisticated choreography that you could come up with to try to optimize the process for sure. Let me ask another question. That is this example of where you were looking for an electrolyte and found a material that might have been good for an electrode. I'm assuming that there was a human that looked at those data and said, "Oh, that looks like that would be good as an electrode," not an AI. Is that correct?
Yeah, that's right. A human find out.
Right.
So we human now find out something unexpected, but I wish some AI find out something unexpected. Yeah, that's our goal. Yeah.
Okay. Yeah, that's terrific. Thank you.
Thank you.
Okay. Next one with a question is Dylan.
Yeah, hi. Thanks
Hi.
for a great talk.
you.
So I have two questions.
Yeah.
One is the reproducibility. Like, do you get the same phase diagram over and over again if you repeat the same material over and again? And the other question is film thickness, because I also deal with thin films. It'd be interesting to see what the effects are of film thickness.
I see. So for the phase diagram, this is sputtering. So you work on thin films, right?
Yeah, we do a lot of MBE, but we've done other materials or other processing as well.
For the sputtering, this sputtering is a very good way to reproduce materials and synthesis, and a very stable technique. So we can reproduce this phase diagram. So the reproducibility is very high, and also the thickness. We deposit thickness like 100 nanometer around. Yeah, that thickness. And then we measure autonomous thickness by fringe using X-ray diffraction, or we try to install this ellipsometry to confirm this film thickness in this.
Okay, so you have not yet looked at property as a function of film thickness.
We haven't. We haven't. We measure this. We don't measure the thickness dependence. We just trying to find good properties. We have to do that.
Okay.
Yeah.
Yeah. Thank you. Are there more questions to Taro? If not, I would like to come back to the question with the data standardization and formats. So in this format standardization, you would also have all the metadata in. Is this true?
Yeah, that's true. Yes, all the metadata is included in this.
So
data.
how did you come to a conclusion like what to include? I mean, I've learned like it's not about really discussion in public because there's no public information. But how did you come to the decision like what is important to include?
I see. So first place, this the like JO or Horiba or those company choose what to include in the data, and then there's a first, that's the first point, and then also there's a free. This data format has like a free area that you can add something more.
Okay.
And then so the data, all the metadata, and then all the like measurement temperature or some measurement acceleration or those data is installed, and then there's a free format part. So that part this user can choose or user can store, and then the whole complete data set is in same format.
Is there also a kind of library about the wordings? Because what we have also heard today is sometimes like people just call it differently. I mean, it's very interesting because like it can be simple words already, which have different ideas, right? So do you have also kind of a catalog to define precisely like what wording you have to use if you want to describe whatever property?
Yes, that's important point. And then this format is there's a like a association of many equipment companies, and there's association, is a national association, and those national associations are preparing those wording, and then that is collaboration with that's collaboration of internationally.
I am impressed that this is all industry driven, not science driven.
Yeah, this is industry
very
driven.
Interesting. It's very interesting. And another question: is this in English or in Japanese?
I think this would be prepared in both English and then Japanese. But I think, yeah, I think about everyone in the world can use soon.
Yes, it's nice. So maybe Japan can help us with the standardization. I hope you're doing a great job with it.
Yeah, I want to do it internationally. So I want to invite many companies and then yeah, so that we can go like a plug and play.
Yes, that would be cool.
Yeah.
Okay, thank you very much. If there aren't any more questions, I would like to thank all speakers again from the day. I learned a lot. I really appreciate all your input and discussions. It was amazing. And we will resume tomorrow again at 1 p.m. Standard Time. And I hope that at least we have a good cross-section of people who have time again to join us, that we have a kind of continuity. I know already that Maria has conflicts.
Sorry.
Yeah, I know it's a terrible time with a lot of proposal writing and conferences in parallel. I understand. Is there anything else what you would like to add, Maria or John?
No, I just want to thank all the speakers and the participants. This was really enlightening and very exciting. Thanks.
A lot of very impressive accomplishments I saw today. So
It's true.
excited about hearing tomorrow's stuff too. This is great.
Yeah.
Thanks. And good night. And for the case of Taro, good morning and good day.
Yes. Have a good day.
Thank you so much for inviting.
Thank
Thank
you.
you. Bye.
Okay. Bye. Thank you.
Bye.